Good morning. Welcome back to all of you. I hope the sessions on probability was fruitful. Today we're going to look at geometry. Now, I can hear you say, oh no. Geometry is one of those topics that most learners find very intimidating. I'm going to use these few hours to explain to you how to approach geometry, how to look at questions, and how to be successful. If you follow these guidelines, I can guarantee you geometry will not be a nightmare anymore. I am going to start with the grade 11 geometry, first of all. This you've done last year, but most probably you don't remember this anymore. And the important thing about the grade 11 geometry is that you will need this geometry to cope with the grade 12 geometry that will come in term 3. So this grade 12 geometry is still waiting for you, but you will not be able to cope with it unless you are up to date with your grade 11. So during the first few sessions, we're going to look only at grade 11 geometry. So with this, the grade 11 students may join us as well. I asked the university to mail the problems that I'm going to discuss with you to your respective schools. Please ask your teachers to give you a printout of these problems. There are problems for grade 11 geometry, and there's another set of problems for grade 12. When we look at these problems, it is very important that you have the drawing in front of you. Otherwise, when you do this, you will not be able to do the problem with me. So please ask your teachers if you may get a copy of these grade 11 problems as well as the set of the grade 12 problems. I'm going to do most of those problems, but not every one. I left a few. There's a few extra additional ones that you're welcome then to do at your own time. Now, for grade 11 geometry, where do we start? And the important thing is we start with theorems. There's a total of 9 theorems within the grade 11 geometry syllabus. Now, I'm quickly going to run over these 9 theorems. And I know you are thinking, but this is totally ridiculous. Trust me, when you do these theorems with me, by the end of this first half an hour, you will remember them. And it's important that you know these theorems. And then, after we've done the theorems, I'm going to show you how to approach a question. So, in the meantime, if you can organize your teacher to get you the problems, we're not going to start with the problems immediately. We're going to start with the theorems, and I hope you are ready. So, let's get going on the grade 11 theorems. The first theorem that you need to know is the theorem that says a line drawn from the center of a circle perpendicular to a chord bisect the chord. Now I want you to read this theorem with me. Just the wording. That's the only thing I'm interested now in. And I want you to think while you're reading, if you understand what is said here. A line drawn from the center of a circle perpendicular to a chord bisect the chord. Now, think of how this theorem looks like. So we say we've got a line drawn from a center of a circle. So we've got a circle, we've got a center, and this line is drawn to a chord. Now remember, a chord goes from circumference to circumference. That is called a chord. Now we draw a line from the center. How do we draw it? Perpendicular to the chord. And you see that's what the theorem said. Line drawn from the center of a circle, perpendicular to this chord, will bisect the chord. Now bisect means it will cut it into equal parts. That means this will be equal to that. So remember, if it's given to you, it's perpendicular, then it will bisect. They can also say to you, it will bisect, then it will be perpendicular. That's what we refer to as the converse. So, perpendicular, it will bisect. And that's the first theorem I would like you to remember. And for this first introduction, I'm only going to discuss with you 4 theorems. So this theorem says, line drawn from a center of a circle perpendicular to a chord, bisect the chord. That is number 1. Number 2 that I would like you to remember is a theorem that is quite well known and very popular, and that is the theorem that says the angle at the center of a circle is 2 times the angle on the circumference. Now, I didn't write down this wording fully. This wording is supposed to say that the angle at the center of a circle is 2 times the angle on the circumference subtended by the same arc. So that means they must come from the same arc. Now, but just in short, let's leave it like that, and I will explain to you. So how does this one look like? This one says that I've got a center, and I've got an angle formed at the center. And that is what we mean by it's subtended by this arc. Now, when I now draw an angle on the circumference, and they must be subtended by the same arc, then this angle will be 2 times that one. So, if this one is 40, that one will be 20. So this angle is twice that one. So angle at the center, twice angle on the circumference. With this one, you must be extremely careful. Very often in a problem, they try to catch you by sketching it slightly different. You will notice that is my angle at the center. But instead of drawing the one on the circumference to that side, above that one, we can draw it to the side. And now it looks pretty weird. You will see that this is the angle at the center, and that is the angle on the circumference. You can see it goes to the center, it goes to the circumference. So always when you're busy with a problem, you look at that arc. This is called an arc. You go to the center and you go to the circumference. Circumference means to the side, to the edge of the circle. So angle at the center, twice angle on the circumference. Now they also sometimes sketch it like this, where they say angle at the center, and then that is the center, and then they extend this line and they draw the circumference. And you can see, it looks completely different to what the very first one looked like. But you can see this angle here is going to be twice that one over there. So it's the angle at the center, circumference subtended by the same arc. Now for the difficult one, they very often give us in problems. And that is where we work not with the acute angle, but we work with the obtuse angle. So if I draw the angle at the center, you see we always think of this angle at the center. Now what about if I work with that angle as the angle at the center, which is now that obtuse angle and not the acute angle? Now where must the angle on the circumference be? So it can't be going to that side like this one, because that one refers to this, but it goes to this side. And you will see they subtended by that long arc over here, that huge arc. So this is the angle at the center, and this is the angle on the circumference. So this angle is twice that one. Now there are these different ways of sketching this that is what makes geometry very often very difficult for learners to identify this in a problem. So it is extremely important that you are aware of these theorems, not only the wording part, but also how it looks like. You need to know, whenever you read this, how does it look like? And I always suggest to learners to do this little summary as I'm doing it for you now. And then, just to test yourself, cover the drawing or put the piece of paper on your drawing. And then you read the wording like this. We put the piece of paper on the drawing. You read the wording and you try to sketch it. And you go to this one. You read the wording and then you try to make the different drawings. And then what you also can do to make sure you understand and know this is to cover the wording, look at the drawing, and look if you can identify it. That you can say, line from the center of a circle perpendicular to a chord bisect a chord. And if any one of these drawings are given to you, that you will be able to identify them. So when you look at this one, that you can say angle at center twice angle on circumference, angle at center twice angle on circumference, angle at center twice angle on circumference. The same thing here. The angle at the center twice angle on the circumference. So every one of these drawings individually you must be able to identify. So both ways, very important that you know these wordings as well as how they look like. So in a theorem, you must know everyone with their respective drawings. And it sounds like a very big task, but it's not so bad. When you read this and you think about it and you look at this, you will make the connection. And the moment you read, you will see this in your mind. And when we get to a problem, then I will show you how we use this to solve our problems. So these are the first two theorems. And I told you we're only going to look at 4 of them to start with. And these are the first 2 of the 4. So the first one again, a line from a center of a circle perpendicular to a chord, bisect a chord. Angle at the center of the circle is equal to 2 times the angle on the circumference. Now, if I put that aside, let's look at the next 2 theorems that is sort of family with those. The third theorem that I want us to look at comes from theorem 2, and this one says that an angle in a semicircle, and you will agree semicircle is a half a circle, is 90 degrees. And I just write it in short again. How does it look like? If I've got a circle and I've got a diameter, remember the diameter runs through the center, and I draw an angle in that semicircle, that angle will always be 90 degrees. So an angle in a semicircle is 90 degrees. And it comes from this theorem 2 that we just did. If you think of that one, this is the angle at the center, but it's now a straight line. So this angle is 180. So what will that one be? 90. Because angle at the center, twice angle on circumference. Can you see how easy that is? So this theorem follows from number 2 that says angle at the center, twice angle on the circumference. And because this is a diameter, it runs through the center, this angle is 180, therefore that one is 90 degrees. The fourth theorem says a radius, and remember what is a radius? Comes from the center, is perpendicular to a tangent at the point of contact. At the point of contact. So that means where the tangent will touch the circle. So let's look at this one. Again we have a circle. Again we have a center. Now we've got a tangent drawn. Can you see there's my point of contact where the tangent touches the circle. Now they say, if I draw a radius to that point of contact, this will always be 90 degrees. Now this is a very important theorem, not only for geometry, but also for analytical geometry. in grade 12, where we deal with tangents and circles, you're going to need this theorem for analytical geometry as well. So this theorem says a radius is perpendicular to a tangent at the point of contact. So when we have a tangent drawn to a circle and we draw a radius perpendicular to that tangent, they're always 90 degrees to one another. They're always perpendicular. Now, that is our first 4 theorems. And I hope you agree with me, this was not too bad. So I just want us to recap quickly on these 4 theorems. And I want to show you something. The first theorem says a line drawn from a center of a circle. It comes from a center, perpendicular to a chord, bisect the chord. The second one said the angle at the center of a circle. And you will notice that it is center of a circle is twice the angle on the circumference. The third one says angle in a semicircle. Now, when we deal with a semicircle, we have a diameter that goes through the center. And then this one, a radius is perpendicular to a tangent. A radius comes from the center. Now, these 4 theorems are only true if the circle have a center. So when you read your question, and the question say there's a center, or O is the center, or this is the center of the circle, then you always need to think of these 4 theorems. So these 4 theorems is our first group. So the name of this group is center of a circle. So if you remember that, we have 4 theorems on the center of a circle. What are they again, if you think about it? If you quickly think with me. Center of a circle. A line from the center, perpendicular to chord, bisect the chord. The second one, the order is not important in which you remember them. But another one, angle at center twice angle on circumference. Another one, a radius perpendicular to a tangent. And another one, angle in a semicircle is 90. So those 4 theorems, in short, the wording, you don't need to remember the wording, the long way of writing, correct way of writing it down. But just short and sweet. That angle at center twice angle on circumference, angle in a semicircle is 90, a radius perpendicular to a tangent, and line from midpoint perpendicular to a chord. And then you remember these 4 theorems, and these 4 theorems work with the center of a circle. Now, I'm going to keep on reminding you of this group of 4 theorems that works with the center of the circle. And as we do the problems, we will think about this all the time. And you will see, if you start thinking that way about these theorems, it's going to be very easy for you to remember them within the next hour or so. You will know them all. But let's go to the next group now. So our first group, center of a circle. Remember, 4 theorems. What is our second group of theorems? And that is the theorems on cyclic quads. So, cyclic quads, or quadrilaterals, the full word for that. Cyclic quads. Now, what is the first theorem? The first theorem says that the opposite angles of a cyclic quad is supplementary. We also refer to it as 180 degrees. So the opposite angles of a cyclic quad, supplementary. How does it look like? So when I have a circle, a cyclic quad, you must remember, is a quad with 4 chords. So these 4 vertices need to touch the circumference of the circle. So this is a chord, that is a chord, that is a chord, that is a chord, and they are on the circumference of a circle, these vertices, and this is called a cyclic quad. So this, and you can name it as well and call it A, B, C, D if you want to. And we say that the opposite angles, so it's this one plus that one will be equal to 180 degrees. And the same with this plus that will be 180 degrees. So it doesn't matter. Any pair of opposite sides. So the correct way is to say a pair of opposite sides of a cyclic quad is supplementary. So that's what we mean by a pair, two of them, the two opposite angles. So that is the first theorem on cyclic quads. What is the second one? The second one says that the exterior angle of a cyclic quad is equal to the opposite interior angle. Now, let's look at this drawing. So if I draw a circle again and I draw a cyclic quad, now we want to know where is the exterior angle. Now, this is extremely important when you look at this theorem to understand that an exterior angle is not one that's drawn here. It must be one of the sides that is extended. Any one of the four sides, if you extend it. So if I extend that side, that is an exterior angle, and it will be equal to the opposite interior. So this is equal to that. If I extend this side, then this angle here will be equal to the one in the opposite segment. So this one equal to this one equal to that one. We can extend on that side, and that will be equal to this. We can extend here, this will be equal to that. So we can get on any one of the sides, if it's extended, you can get an exterior angle which is equal to the opposite interior. And that is our second theorem on cyclic quads. What is the third one? The third one says that angles in the same segment are equal. Now again, I just wrote it down short for us to fit it in. How does this look like? If I draw a cyclic quad again, inscribed in a circle, then if I draw diagonals in it, within that one, then we have that angles in the same segment. Now, they must also, what this theorem say, when you read it in your textbook, it will say that they must be subtended by the same chord. So you can see there's a chord. And from this chord, which is on the circumference, those vertices, you go to the circumference and you go to the circumference from the same 2 points. So this angle is equal to that one. It's angles in the same segment. Now, when you turn around your drawing, you will find more of them. So you can say that this one will be equal to that one because they subtended by this chord. Always remember, from the vertices on this chord, or from the, if you look at this particular chord and you go to the circumference, and you take the same chord and you go to the circumference, then those two angles are equal. They're in the same segment. And we can also look at it in many different ways, and we can say that this one will be equal to that one. So this is equal to that for the same reason. They are subtended by this chord. This is equal to that, subtended by that chord. This is equal to that, subtended by this chord. So it doesn't matter. It depends what you are looking for. This theorem, as long as they subtended by the same chord and the angles on the circumference, they will be equal in size. So these are the three theorems that you need to remember in terms of cyclic quads. So whenever our problem is about a cyclic quad, what do you need to remember? First of all, that opposite angles are supplementary, that the exterior angle is equal to the opposite interior, and that angles in the same segment equal. So three things that you need to remember. You need to remember how they look like so that you will be able to identify it in your drawings in the problem that we're going to do. So, again, if I can recap, three theorems on cyclic quads: opposite angle supplementary, angles in the same segment equal, and exterior angle equal to the opposite interior. And I hope you still remember the first four. The first four on center of a circle. And what did we say about them? There were 4 theorems on the center. First of all, angle at center twice angle on circumference. Secondly, angle in a semicircle is 90. Thirdly, a radius perpendicular to a tangent. And the fourth one, line drawn from the center perpendicular to a chord bisect the chord. When we look at cyclic quartz, what are the 3 theorems on cyclic quartz? First of all, opposite angles are 180 degrees. Then the exterior angle equal to the opposite interior. And then the third one, angles in the same segment are equal. And I think you agree with me. We've done quite a number now, and it's not so difficult to remember. Don't try to remember all of them. Remember, 4 of them on center of a circle, 3 of them on cyclic quartz. Are you ready for the last group of 3 theorems? In this group, we look at theorems based on tangents. So my heading for these ones are tangents. And there are 3 theorems on tangents that you need to remember. Remember, 4 theorems on center of a circle, 3 on cyclic quartz, 3 on tangents. Number 1, and we did this one already. This one I've put in 2 groups. I've put it in tangents as well as in center. And that is if you have a tangent, the radius will be perpendicular to the tangent. So I'm not going to write it down fully. I'm just going to say here that radius perpendicular to tangent. And that is how we will write it down as a reason as well, because we've discussed this theorem already. Just remember, this theorem is part of 2 of the groups. So radius is always perpendicular to a tangent at that point of contact. The second theorem is the very famous one, and that is called the tan-chord theorem. And that is the angle between a tangent and a chord. Remember, it's the angle formed between a tangent and a chord is equal to the angle in the opposite segment. Now, the wording of this theorem sounds always horrible because this opposite segment is not very clear to us. But let's sketch it and let's see if you can see what this means. That is a tangent drawn to a circle. If I have a chord, then you can see that the angle formed between the tangent and the chord is this angle. And now I complete a triangle there. So this angle will be equal to the angle in the opposite segment. So angle between a tangent and a chord is equal to the angle in the opposite segment. One must also remember that this theorem sometimes look a little bit different. And that is where they put it to that. This is now your point of contact. And then they complete the triangle over here. And now you will notice that this angle, which is now an angle that looks like greater than 90 degrees, will be equal to that one. So this will be equal to that. Now, an angle between a tangent and a chord is equal to the angle in the opposite segment. Angle between a tangent and a chord equal to the angle in the opposite segment. This is for an acute angle, and this is for an obtuse angle. So be aware the different ways they can draw it. This one, we most of the time are getting used to this one, and easy for us to see it. But this one, not always so easy to see in a problem. So 2 theorems up to now on tangents. What is the third one? The third one is that theorem that is very seldom in a problem, but just from time to time they like to bring this theorem in. And that is the third one that says 2 tangents drawn from the same point outside a circle. So we draw two tangents from the same point outside a circle are equal in length. Now, how does that look like? So I have a circle. I've got a point outside a circle. From this point, I draw a tangent. And from this point, I draw another tangent. And as you can see, I've sketched two tangents. This is a tangent from that point to the circle. It touches the circle there. It touches the circle there. And those two lines will be equal in length. So when we join those 2 points of contact, that will be an isosceles triangle. That is what this theorem is trying to tell us. So how do you know this theorem? You're going to need it. The moment that there are two tangents drawn from the same point, you can already look out for this theorem. Can we just quickly go over these tangent theorems one more time? The first one, radius perpendicular to a tangent. The second one, angle between a tangent and a chord equal to the angle in the opposite segment. And then the third one, two tangents drawn to a circle from the same point equal in length. So those are the three theorems on tangents. Do you still remember the three theorems on cyclic quads? Let's quickly have a look. Opposite angles, supplementary. Exterior angle equal to the opposite, interior. Angles in the same segment are equal. Then the four theorems on center of a circle. 4 of them. Let's go over the 4 theorems again. Line drawn from a center of a circle perpendicular to chord, bisect the chord. Angle at center, twice angle on the circumference. Remember, it can be the obtuse one as well. Angle at center, twice the angle on the circumference. Then the third one. Angle in a semicircle is 90 degrees. The fourth one, radius perpendicular to a tangent. So there are your 3 groups of theorems. And please make yourself a little summary like this one. And you can see mine, I've done it quite big. And it's not so necessary to make it extensive, these summaries. So write down for you the 3 groups of theorems. First group, center of a circle. The second group, cyclic quads. The third group, on tangents. And please remember each one of them. And I'm going to revise them with you as we go along. I hope you are now ready so that we look at our first problem and we're going to use these theorems. Now, this question, if your teacher managed to give you a copy of these questions, I would like you to look at the drawing of this one. At the top it says question 7. These questions are from old exam papers, so it's the kind of questions you can expect in the exam. And I'm going to start with you with the ones that's a little bit easier, and we're going to build it up to more difficult ones. Now, why do I say these ones are easier? Because an angle is given to you. You can see it clearly, 36 degrees. And that means we're going to find other angles. Now, when you approach a geometry question, and I want you to listen very carefully, you will notice that I've put a piece of paper over my questions. So please cover your question, either with a piece of paper or with your hand. Don't look at the questions yet. It is extremely important that we first analyze our drawing, see what we have before we look at our questions. Most of the students, they look at the drawing, then they read the question, and they hope they're going to see the solution. It doesn't work that way all the time. Sometimes you're lucky and it may happen, but not all the time. So let's start with this first question. This question says, in the diagram, O is the center. Now, I always say to students, the moment you read that O is the center, you stop right there. And you remind, in your mind, you think of the 4 theorems on center. Can we quickly think of them again together? Center of a circle. Line drawn from a center of a circle, perpendicular to a chord, bisect a chord. Is that theorem here? Now you look for that theorem. There's a line from the center. There's from the center. But no one is drawn to a chord. You can see there's a chord, there's a chord, there's a chord, there's a chord. But no line is drawn to a chord. So that theorem is not here. I don't need to worry about it. The second theorem was angle at center is twice angle on the circumference. Now, when you look at this one, and you can even turn your drawing around if it makes you feel more comfortable. Can you see there's an angle at the center? Because O is the center. From SW. You go from SW to the center. Now, from SW, is there an angle on the circumference? And many people think it's this one. But you can see this one does not come from SW. It comes from SP. So they're not subtended by the same chord. So they must be subtended by the same chord. That is O, and the center, that's angle on the circumference. So angle at center, angle on the circumference. So if that is confusing you, let me turn it around, and now it looks like when we did it. The angle at the center is twice the angle on the circumference. And this is the one that goes to the side. And you will remember I gave you that one possible drawing. Angle at the center, twice angle at circumference, or sometimes angle at the center, twice angle on circumference. Center and circumference. So this one is twice that one. So I want you to think now with me. So we've got this theorem in this one, that the angle at the center, this one, is twice that one. So what is the size of this angle? That one is 36. What is this one? And I know some of you are now able to answer this. And I want you to say it. What is this angle at the center if this one is 36? Remember, to find this one is twice that one. And are you all happy that this one is 72 degrees? And there we've got the angle at O already, the acute one, subtended by SW, because this one is 36, that one is 72. Also something to remember, this is a radius, and that is a radius. So these two lines are equal in length. So that is in an isosceles triangle. We may need that later. So the moment you have radii, you may indicate that they are equal. Now, so I've got the second theorem. The first theorem didn't work. The second theorem worked. The third one, angle in a semicircle. There's no diameter. There's no line drawn through the center. So that theorem is not there. The third theorem is radius perpendicular to a tangent. There's no tangent here. So that theorem is not there. It's extremely important that you look for every one of those when you deal with the center. Now we continue. We say PWSR is a cyclic quad. Now, do you remember I told you that there are 3 theorems on cyclic quads? The first one is opposite angles are supplementary. So we know that is your cyclic quad, that's W plus R is 180, and that S plus P is 180. Remember, I'm not going to write it down on the drawing because it's going to make the drawing quite messy. But you can write it down on the side if you want to, that you must remember the opposite angles are supplementary. Now, the second theorem was an exterior angle of a cyclic quad. And you can see no one of the sides are extended, so there's no exterior angle. The third theorem was angles in the same segment. Now, angles in the same segment is where we have diagonals. And you can see we have a diagonal on this one, but we don't have one on this one. So there are no angles in the same segment. Many people say that this maybe is equal to that because it looks like it. You can't do it if it looks like it. You need to know if this one is drawn to R. This one is drawn to O, not to the circumference. Remember that theorem was if it's drawn to the circumference, then that theorem is going to work. It looks like this, if I can remind you. So this angle is equal to that. So they must be subtended by the same chord. Then they are equal. Now, you will notice that when we look at this one and that one, that this angle P2 is subtended by SR. But the one at W1 is not subtended by this, it's subtended by that. So they're not subtended by the same chord. So that means that we have only the one theorem that we can use, and that is the opposite angles are supplementary. What else did they tell us? They told us that BSWO and OS are drawn, just those lines that's drawn. And then they gave us something very important, that PW is parallel to OS. PW is parallel to OS. Now, if two lines are parallel, and that you know from the earlier grades, there are three things that you need to remember. And first of all is alternate angles. Now, when we have lines that is parallel, if I have two sides parallel, then we know that this angle will be equal to that one. We call it alternate. And we also have, if two lines are parallel, that this angle is equal to that one. They are called corresponding. And we can now look for these. So you can see this line is parallel to that one, and there's a line that intersect. So do you agree with me that those two are corresponding? Not corresponding, sorry, but alternate. And this one, alternate with that one. So if this is 36, you're happy if I say that one is 36 degrees, because it's alternate angles. If this one is 72, that one will be 72 degrees, because they are alternate angles. And we don't really have any corresponding. And then the third group that we have on parallel lines is if two lines are parallel, then the co-interior angles equals 180. So this plus that, and that one is not present here. So by doing this, by reading through our given information that we have a center, we think of the four theorems. Cyclic quad, we think of the three theorems. There are no tangents here, so those theorems are not applicable here. We try to find as much as possible by doing all of this. And now we are ready. So you may even now, if you want to, try to find more angles here. You see there we've got 36 and 72. That W1 we don't know. Is it possible to find it? That one is 36. Can we find that one? So once we've got W1 and W2, this plus that is 180, because it's opposite angles of a cyclic quad. So all those ones are possible to calculate now. And you can do that before you start. But let's see, first of all, what is our first question. And our first question is, and I'm just going to keep the drawing there, and that is to find the sizes of the following angles. 7.1, they ask us to find SOW. So this is this angle at O. Now, you can see we wrote it down already. So, how difficult can it be to do this question? We're going to say that P1 is equal to 36 degrees, and that is given to us. Always remember your reason. So I start with what I have. That 36 was given to me. Remember, that 72, 36 was not given. This one is given to me. So what is that angle at O? We call it SOW. So we go SOW, this angle, is equal to 72 degrees. And what is my reason? My reason is angle at center of circle is equal to 2 times angle on circumference. And you write down that reason. Angle at center is twice the angle on the circumference. And believe it or not, we are finished with the first question. And I hope you agree with me that this is not so difficult. Once you think correctly, and if you approach this correctly. Let's look at the second question. In the second question, they ask us for W2. W2. Now, you notice that I've already wrote 72 in there. Now, how do we know that is 72? And that 72 I've got from this 72. And that 72 we've done already. So we can start by saying that SOW is 72 degrees. And that's already proven. I don't need to do it again. I just say it's proven. Now, how do I get to this one? So now I say W2 is 72, and the reason is alternate angles. And then you need to say which lines are parallel. And that is, the two lines that's given parallel is PW, OS. PW parallel to OS. So we just tell them that is alternate angles because the lines are parallel. And then we have this answer. And we are finished. And we go to the next question. There's a total of 4 questions, and we are now at number 3. Now, in number 3, they ask us for OSW. Now, let's look where OSW is. They want OSW. So look carefully. OSW. So they want this S1 and 2. S1 and 2 is what they are looking for. Now, the first thing that you need to realize, you remember that I've put these 2 little lines in to say that these 2 sides are equal. Now, because of radii, if these sides are equal, you agree that this angle will be the same as that one. So this 1 and 2, this OSW, is the same as W1. So that is where we're going to start with this question. We're going to say that OSW, the one they are looking for, is the same as W1. So that OSW is the same as W1. Now, how do we get that? And that is the angles opposite equal radii. So what does this mean? I've got equal radii, and it's the angles opposite them. Angles opposite equal radii. So it's an isosceles triangle because of the radii. Now, how can we find these 2 angles now? So this is what I want, but it's the same as this one. So how do I find them? Now, if they're the same, and they're part of a triangle, and we know angle O is 72, you will agree with me that I can find both of them, or any one of them, by subtracting 72, this angle, from 180, and then we will get those 2 angles. So I can say that OSW plus W1 is equal to 180 minus 72. So then I calculate both angles. And the reason for it is angles of a triangle is equal to 180 degrees. Because this plus that plus the 72 is 180. So if I subtract 72 from the 180, I get both those angles. And what is my answer here? If I subtract 180 minus 70 is 180 minus 70 is 110, minus 2 is 108 degrees. So what is OSW now? So OSW is equal to 108 divided by 2, which is 54 degrees. And the reason for that, we said it already, because it's in isosceles triangle. And there we found our answer. Now, not all the steps are necessary. I just do it thoroughly so that you follow me all the time on what I discuss here. But rather write down more than less. Many people just want to write down an answer, and if the answer is wrong, you will get 0 in an exam. So, the last question, 7.4. They ask us to find angle R. Angle R. Now, before we write this down, if I may just show you first of all. If I want angle R, you agree with me, we just found OSW. We also found W1 because they are the same. And you remember that was 54. So is that one 54. So if this is 54, W1, W2 is 72. And do you agree that this angle plus this one is 180? So how do I find R1? And I'm just going to write it down here so that you can see. So to find R1, I'm going to say that, so to find R, I'm going to say that W1 plus R plus W1 plus R plus W2. Sorry, I was supposed to put that together, but it doesn't matter. W1 plus W2 plus R is equal to 180 degrees. And the reason is opposite angles of a cyclic is equal to 180. So this angle plus that one plus that is 180. Do I know W1? Yes, so I say R1, just R, plus W1 is 54, plus W2 is 72, is equal to 180. And now you agree, you will be able to write down angle R. Was not so bad, ne? It was a 3-mark question. You just need to realize that this plus that is 180, opposite angles of a cyclic quad. We calculate that one before because we worked out that one. This one we worked out before, so we don't need to show it again. And we add those two, subtract it from 180, and your answer for that is 54 degrees. And there you are, finished with this question. The total marks of this question, of this particular question, is 10 marks, and I hope you agree with me that this is not so difficult to answer. But what is required? You need to know those theorems. Don't try to remember all of them. Just remember them in groups. Use them in those groups. So I'm going to repeat. If you read anything about a circle, a center of a circle, you think of 4 theorems. If you read of a cyclic, or you see a cyclic quad, you think of 3 theorems. We will get to the tangents now. If you see one on a tangent, or there is a tangent drawn, think of the 3 theorems. So, I hope you are ready for our next question. Let's go for the next one, and I'm going to follow the same approach. Don't rush through these questions. They're worth lots of marks in the exam. Cover the questions when you start with your hand over a piece of paper. Read carefully. Think of your theorems and find whatever is possible. And then you answer by writing down with your reasons. And I promise you, geometry will really be fun. Let's look at the next problem. My next question that I would like to discuss with you is on, you will notice that on the questions given to you is number 8.2. And I'm just going to cover the questions again. So please don't look at the questions at the bottom. And we only look at the sketch, and we look at the given part. And we see what is present in this drawing, what can we find, and then we go and we answer the 2 questions. There are 2 questions on this problem. They say in this figure below, O is the center of the circle. Now, O is the center of a circle. Now, immediately we want to rush into the one obvious theorem that we can see, which is okay. You can go for that if you would like to. But what I would like you to do is not only to look for the theorem that says the angle at center, but also to think of the others for in case they are there. Now, first of all, there's no line drawn from a center to a chord. There's a chord, there's a chord, there's a chord, and no one is drawn. So that theorem is not there. The second theorem is there, and that is the one that says angle at the center twice angle on the circumference. So if I just turn it a little bit, you will notice that with the chord Ln, we have an angle at the center of 100 degrees given to us. Does this also give us an angle on the circumference? And now you must be careful, because we don't have an angle on the circumference here. Not from this chord in that direction. But what we do have is we have an angle at the center, the Ln1, And that LN forms an angle on the circumference. You see it? That is that awkward one. So what we know is that this angle here, and that one is 100, remember they're together 360, so this one is 260 degrees, will be twice that one. And if this is 260, what is that one? That one will be 130, because twice that one is this one. So this is the obtuse one that I told you about right in the beginning, that I said that you must be very careful. It's sometimes extremely difficult to notice this particular question. And I just want to show you this one again to remind you. This was the one who looked like that. The angle at the center is twice the angle on the circumference. And if you want to, you can look at it the other way around. You can say angle at the center, twice angle on the circumference. Now, if you think of that one, look now at this one. If I can show you both. Angle at the center, twice angle on the circumference. The angle at the center, twice angle on the circumference. And the more you look at them, the easier you will identify them. Now, that is the first theorem that we can see, that this is twice that. This one is 100 given to us. Now, that was the center of a circle. What other theorems? Angle in a semicircle, it's not there. A radius and a tangent, it's not there. So only that one theorem was present. Now they say these are points on the circumference of a circle, KLMN. KLMN. Now, these 2 points are not joined, but it doesn't matter. If you imagine a line there, this is a cyclic quad. Are there any exterior angles? No. Opposite interior? Not quite, because those lines are not joined. But angles in the same segment? Most probably. Let's have a look. So if I turn it like this, and I take this as my chord, even there's not a chord drawn here, this KN, and I go to the circumference, then it's L2 and 3, and I go to the circumference, and it's M1. So M1 is equal to L2 and 3. So what you can do is, and I don't want to mess up our drawing, but is maybe to draw 2 little lines so that we can just say that this angle, this M1, which is formed by Kn, is equal to that one. I draw 2 lines there as well. So this angle will be equal to that one because of angles in the same segment. No theorems on tangent, so they're not there. It's also given to us that LM is equal to MN. So these 2 lines are equal, so that means these 2 angles will be equal. So at this point in time, we don't know what they are, but we know this whole angle is 130. Ne? So these 2 will be the same. Remember in the previous question we did it. Subtract the 130 from 180, divide by 2, then we can find those 2. And we can do that, so what will it be? 180 minus the 130 is 50 divided by 2. So I want to claim that those 2 angles will be 25 each. And as you can see now that we've got those 2 angles as well. And that is because those lines are equal. We already used the 100. This angle is 100 degrees. And now what you must remember is that this is the center of the circle. So this is radii. So there is also an isosceles triangle. So that means we can find those 2 angles. Because it's 100, you subtract from 180, so it's 80 divided by 2, so they will both be 40 degrees, those 2 angles over here. So as you can see, we can find quite a lot of them by just thinking and looking at what is given. This radii, many people miss, and they don't think about it. Remember, that is one of the things that you must remember if center of a circle is given to you. You look for radii. You think of the 4 theorems, and you look for radii. So those are the important things. Let's now look at our first question. Our first question asks us to find the size of LN. LMN. LMN. And you can see we found that already. How did we do it? So now you need to think carefully. How did we find this angle? This LMN. It is this M1 and 2. And what we've done was to find this, what we call the reflex angle. So we call it reflex angle O. So to refer not to this one, but to the reflex one, is equal to 360 minus 100, which is equal to 260. So this is my reflex angle. All right, and for a reason, we just say angles around a point is equal to 360. So those angles add up to 360. Now we say that LMN, that is what they want, LMN, some people like to call it M1 and 2, you can do that as well, is now equal to 130 degrees. And your reason for it, angle at center is equal to 2 times angle on the circumference. And there we finish the question. So it is double this one. So this one is, the angle at the center is twice that one. So this is 260, that one is 130. And there we finished with our first question. What is our second question on this one? There is the drawing, and there are the questions. So how will we do this second one? If I just put my piece of paper here so that you can see what I write. We want 8.2.2, and they ask us for LKM. LKM. Now, this angle LKM, we may just call it angle K as well, because that is the only angle at K. So instead of calling it LKM, we can call it angle K for short. Now, how do we find angle K? And this is now very important that you look at this one, because we didn't put anything in there. So how will we get to this one? And now you can see this angle is on the circumference. It is subtended by LM. Is there any other angle also subtended by LM? If you look, there's my LM. And this one subtended angle K, but it also subtended N1. So I hope you agree with me that N1 and angle K will be equal. So that we can say angle K is equal to angle N1. And the reason is angles in the same segment. Because remember, those 4 points are on the circumference of a circle. So with this chord, I get angle K. With this chord, I get angle N. Now, I know these two angles are equal, but now I know, I wrote down already that N1 is 25. But how did I find it? Remember, this was given to me. So I'm going to use the fact that the two sides are equal, and with the isosceles triangle, then those two angles will be equal. So I can say that N1 is equal to 180 degrees minus the 130. Remember, this angles of a triangle, 180, minus the 130 divided by 2, because they will be the same. And this will be equal to 25. And what is my reason? My reason, two reasons for this. First of all, angles of triangle is equal to 180 degrees. Secondly, we say that LM is equal to MN given. that those two sides are equal. So it's an isosceles, you can put with isosceles triangle. So if I just move it a little bit to the side, then you can see. So how did I find N1? Remember, this is a triangle. I know this is an isosceles triangle. So I know this is 130. Subtract it from 180 is 50. Divide by 2, so I get both of them. This one is the same as that one. So now you say, therefore, angle K is equal to 25 degrees. You don't need to give a reason because you already said they are equal, and what is the reason. So they equal, that is my reason. Then you found the one, and that gives you the other one. And with that, we are finished with this question. So I want to remind you that when you look at geometry questions, please, first of all, don't look at the questions. Look at your given part. Look at your drawing. And then when you read, O is the center, remember the 4 theorems. When you have a cyclic quad, remember the 3 theorems. When you have a tangent, remember the 3 theorems. Write down whatever you can find on your drawing, next to your drawing, write it down. Then look at the first question, look at the second question, and answer them. You will not believe how easy it will become. Our next problem is a problem where a tangent will be part of it. But for this moment, we're now going to take a 10-minute break so that you can stretch your legs and just think of what we've done before we look at more questions. I see you within 10 minutes' time. Welcome back. We discussed the grade 11 theorems this morning, and I'm going to remind you again of those 3 groups. Before we do that and continue with our next problem, there was a question on question 7 that we've done earlier. And one of the learners asked me to explain 7.3 again. So before we continue, can we go back to question 7, number 7.3? So if you look at that drawing, you will now see it on your screen. This is the question that we did, the very first one. Question 7, and this circle was given to us. Remember, if I can go over this again, O is the center of the circle. So there was an angle at the center. There's an angle on the circumference. That's to the side. So 36, that will be 72. There's a cyclic quad. That is a cyclic quad where opposite angles are supplementary. And then they say those 2 lines are parallel. Those 2 lines are parallel. So we have alternate angles, 36 and 36. This 72 comes from the angle at center twice angle at circumference, and then alternate, that is 72. Just to brush up again what we have. Now, in the first part, they ask us to find SOW. And then they ask us to find W2. And then the question is on OSW. How do we find OSW? So, let's look again at 7.3. And I want you to focus with me now. Remember, SOW we've got already. SOW, that is the 72. W2 we have already, that is 72 because of alternate angles. Now we're at OSW. OSW. Now, OSW is the same. If this OSW confuse you, think of it as S1 and 2. Because that S1 and 2, remember that is 36 degrees, né? Angle 1, 2, 3. 1 and 2, that is OSW. We talk about that angle, this angle. Now, what did we do? To find OSW, we said that OSW is the same as W1, You see, this angle is the same as that angle, this one, because of the radii. This is an isosceles triangle. So those two are equal, and the reason of it is isosceles triangle, and we can say equal radii. So this is equal to that because of radii, therefore those two angles will be equal. Now what are they? You notice that I've wrote in 54 already, but we must now find that 54. We know that this is 72. So to find OSW, what do? We take 180 degrees, we subtract the 72, and we divide the answer by 2. Because those two angles will be the same. So once I subtract this from 180, I get those two angles. If I divide by 2, I get that one. And if you calculate this, you will now get 108 divided by 2 is 54 degrees. And the reason is angles of a triangle is equal to 180 degrees. And there we find OSW. So, if you follow the first time around, it is not too difficult. Please remember, this side is equal to that one. And this is what many people miss. And then they don't know how to find that OSW because they didn't realize this is an isosceles triangle. Remember, this 72 comes from the 36. And then angles of a triangle, you can get those two. You divide by 2 because they are the same. And that is the reason of the radii. I hope this explains this OSW to you. There is another question that I would like us to look at again. And one of the learners asked that we look at our second problem, which is the 8.2. And he asked for 8.1, but there's not a 8.1. There was only a 8.2.1. So I assume it is this one. So please, if that is not the correct question, I'm going to discuss this. Please let us know, and then I can discuss the correct one with you. But I take it that you want number 1 from this 8.2 question. Let's just, before we do it, let's just quickly recap on this question. What did we do? Remember, there's now lots of writing here because we've done it already. I say in this figure below, O is the center. When O is the center, I look for my theorems on the center. And of course, we have angle at the center. Now, this 100 doesn't have an angle on the circumference. But what is important, if you turn it, that this angle here, we call it the reflex angle, 260, is twice that angle, this one. And that is 130 degrees. 260, 130. So this number 1 and 2, this one is 130 degrees. And that is the reason for that is angle at center twice angle on circumference if we look at the reflex angle. So if I can show this to you again, is that if I have a center and I look at this angle, not that one, this angle at the center, we have it as 260. And that is the one on the circumference. And that one will be 130. And I want you to compare this one now to that one. And you will see why that angle is 130. So 260, 130. Remember, we are very used to the common way of angle at center, where we work with the acute angle, it's twice angle on circumference, but we also can work with a reflex angle, twice angle on the circumference. Now, in our first question that you ask, LMN, that is what they wanted us to do. So if I turn this drawing again, Can you see that looks like an angle at the center, but this one doesn't have, because if you look at that, there's no angle on the circumference of this one, but we have it to that side. Now, if I go to that side, I can't use this one because it's on the inside. I must use the reflex one. So the reflex one is equal to twice that one. They both subtended by this. This is the angle at the center, but this one is equal to angle on the circumference. So make sure that you know this drawing. This drawing, like I said, very popular in the exam. Students find it sometimes very difficult to see. So this is 100. This is 260 because of angles of a triangle. If this is 260, that is 130. Your reason, angles of a triangle. Not angles of a triangle, but angle at the center equal to twice angle on the circumference. I hope I've done the correct question, what you requested. So let's now look at the next question. If you look at this one, you will first of all notice, without reading, doing anything, you will notice there's a tangent. It is so clear. So definitely the theorems on tangents will be present now. So where do we start? Again, cover your questions. Let's read. Let's think of our theorems. This one is called question 8. And let's see if we can cope with this question. This question got 5 sub-questions, so there's quite a number that we need to answer. And let's start. Remember, if you read O is the center of a circle, then you stop right there and you think of the 4 theorems. The 4 theorems. First one, line drawn from a center perpendicular to a chord, bisect a chord. Angle at center, twice angle on circumference. Angle in a semicircle, 90 degrees. Radius, perpendicular to tangent. Those 4, you need to remember. Let's see if any of those 4 is present here. Don't worry about the tangent yet. We will still get to the tangent when we read that. So we only look for those. First of all, you will hopefully notice that there's a center, and this center doesn't have any line drawn to a chord. So that theorem is not here. But there's an angle at the center. You can see UK from UK. And there's the angle on the circumference. So angle at center, angle on circumference. So I hope you agree with me that this angle here, this one, will be twice that one. So this angle is twice that one. Angle at center, twice angle on the circumference. So remember that. That is very important. Now, you also notice that there's no diameter. So that theorem is not here. But you notice that there's a radius. There's a tangent. So that will be 90 degrees. So that theorem we haven't had before. And many people miss that theorem, that the radius is perpendicular to the tangent. Now, they say that O is the center of this circle, KTUV. KTUV. And that is now a cyclic quad. Now, when I think of cyclic quads, I think of opposite angles, supplementary. 120, that one is opposite. Are you happy that this one is 60? Because they add up to 180. If this one is 60, we already said this one is twice that one. So this one will be 120. 120. Not because of this 120. 120, that one will be 60. Opposite angles of a cyclic quad. If this is 60, this will be 120. You times by 2, you get this one. Now you agree. That is radii. So we will be able to find these 2 angles. The 120 from 180 is 60 divided by 2. They are both 30 degrees, these angles. We don't know if we're going to need it. I'm just writing it down. Now, that angle is 90. This one is 30. This one is 30. That one is 48. And that is because of the cyclic quad that we have. Are there any exterior angles of a cyclic quad here? No. No one of the sides are extended. Are there any angles in the same segment? And the answer is no, because that one, there's no diagonal drawn here. There's a diagonal, but not one there. So no angles in the same segment here. Now they tell us that this is a tangent. Now I think of my theorems. The first theorem on a tangent is radius is perpendicular. I used that already. And then, of course, the famous one, and let me turn it around so that you can look at it this way. We spoke about the tan chord theorem. Now I want you to look at this very carefully. Because of the many lines, it's not so easy to notice. Now, if you look at the line, the angle between the tangent and a chord, this angle, do you agree with me that this angle here, K1, if I complete the triangle, will be equal to that? And this one is 48 and 30. So this one will be 78 degrees. And I want you to make sure to see where do I get the 78 from. This 78 is coming from that 48 which was given to us, and this angle of 30. Remember the 30, why? Because this is 120, because that is 60, this is 120, and this is an isosceles, so 30, 30, angles of a triangle, and then that whole angle there, the 48 and the 30, if I complete the triangle, gives me K1, which is 78. Now if this one is 78, remember 1 and 2 is 90. That means I can find K2. And K2 is 90 minus 78. And I think you will agree with me. That sounds like more or less 12 degrees. No? 12 degrees for that one. Because 78 plus 2 is 80 plus 10 is 90. So there I calculated a few more angles. Now, what else do we have? We also have a triangle here. Remember the one that I showed you earlier on this theorem that I told you they sometimes use, but it's not that obvious. And I just want to show you the sketch again. I did it like this. We just use this one, is equal to that. What about this angle equal to that one if you have this triangle here? And there is an obtuse angle. So if you look at this problem, you will notice that there is that obtuse one. And if you complete that triangle, this whole thing is equal to that. So this 120 must be equal to all of those. Is it true? That is 90. That one must be 30. We've got it already because 90 plus 30 is 120. So we have that. So we found many of these angles, and most probably it helped us to answer our questions. Hopefully you are with me on how I found these particular angles. Just remember, how do I do it? When I see center, I think of my 4 theorems. When I see a cyclic quad, I think of the 3 theorems on cyclic quad. When I see tangents, I think of 3 theorems on tangents. Let's now look at the first question. The first question is they ask you for angle V. Now you can see there's already written 60 degrees in. We just need to remember how did we get to the 60. And that is not so difficult. So let me quickly write it down for you. In 8.1, let's go over it again. I'm going to say that angle V is equal to 60 degrees. And my reason is opposite angles of a cyclic quad equal to 180 degrees. This one is 120. That one is 60 because the opposite angles of a cyclic quad is supplementary. And there you finished. It's 2 marks. 1 for your statement, 1 mark for your reason. Let's look at the second question. And in 8.2, they ask us for KOU. Now let's look at KOU. KOU. And it's this angle, KOU. Can you see it's 120? How did we find it? We say angle V is 60 degrees. And that's already proven. And now we say KOU is equal to 120, which is that 120, it is basically the 2 times the 60. And the reason for that is angle at center 2 times the angle on the circumference. So that is how we find it. Short and sweet. This one, opposite angles of a cyclic quad. This one, twice this one is this one, because angle at center, twice angle on circumference. And that gives us KOU. And that is another 2 marks. Now they ask us for U2. Now when you look at your drawing, you will see that U2 is this one, which we said it's 30. How do we find U2? So we go for 8.3. If I can just move it up, that you can see the drawing. Please look at the drawing all the time. We want now, what is the question now is to find U2. How do we do it? We know that U2 is equal to K3. U2 and K3 are the same. And the reason is isosceles triangle equal radii. Because we've got radii. So why is it isosceles? It's because of the radii. It was not given to us equal. So we need to know that these are radii, and therefore it's an isosceles triangle. So this, now to find this U2, we take 180 degrees, angles of a triangle. We subtract the 120 because we've already got that one. And we divide the answer by 2. And that gives us then 180 minus 120 is 60, divided by 2 is 30 degrees. And the reason is angles of a triangle is 180 degrees. And there we've got angle U2. So we are finished with that question as well. So the first 3 questions, first of all, they ask us for V, opposite angles of a cyclic quad. Then they ask us for this angle at O, which is the angle at center, twice angle on circumference is 120. Then they ask for U2, radii, they are isosceles, so therefore angles of a triangle, it will be 30. Let's now look at the 4th question. And in number 4, they ask us to find K1. Now, K1, you will notice, is next to that K2, K1, 2, 3. Now, K1, K2 is equal to 100, equal to 90. Sorry, because the radius perpendicular to a tangent. But they want K1, that's 78.1. Now, how do we find that K1? How will we write it down? And think carefully. How did we get K1 to be 78? This is now 8.4. How do we get that? Now, what you will remember, if I may turn the drawing again so that we look at the tangent horizontally. We said that this K1 is an angle between a tangent and a chord. And if I follow this chord all the way back, that this angle K1 will be equal to the angle in the opposite segment. You can see to this one here, that one. So this angle is equal to this one. Now this is 48 given, 30 we worked it out, so therefore that one is 78. And that is what we're going to write down for K1. So when I write down this K1, I will say that angle K1 is equal to 48, it was given to us, plus 30 degrees, that is U2 that we just did in the previous one, and that will be equal to 78 degrees. And what is your reason? We say the tan chord theorem. And that's all that you need to write down. Quite acceptable in the exam that you use the reason tan chord theorem. So that K1 is equal to 48 plus 30. And you are finished with that question. Now for the last question here, and they ask us for K2. So first K1, then they ask us for K2 in 8.5. K2, you will see I wrote down there 12. Now how do we get to the 12? It's also very easy. We will say that this was K1, sorry, I've left that out. K1 was 48 plus 30, which is 78. Now we say K1 plus K2 is equal to 90 degrees. Remember, K1 and 2, we said is 90 degrees. Your reason is radius perpendicular to a tangent. But we found K1. So what is K2? It is 90 minus 78, which is 12 degrees. And that is all that you need to do. They ask you for K2 now in this question. Remember the last two questions, K1 and K2. K1 we did. K1, angle between a tangent and a chord equal to the angle in the opposite segment. So we add those two. This angle is 90, 1 and 2. That is 78. What is number 2? It's 90 minus 78 because the radius is perpendicular to a tangent. So this is our first question where all three groups of theorems were present within this problem. And you will notice there was the angle at center twice angle at circumference. There was the theorem on a cyclic quad, the opposite angles of a cyclic quad. There was two theorems on radii, radius perpendicular to a tangent, and then the tangent one, the angle between a tangent and a chord equal to the angle in the opposite segment, or what we refer to as the tan-chord theorem. So quite a number of theorems involved in this problem. So this question, extremely important that you will be able to do a problem like this. And that is how the problems become more difficult. They use more and more theorems within a problem. And people sometimes miss some of these theorems. I remind you again, always remember, if there's a center, not only the four theorems, that there will be radii. Secondly, this theorem that says radius perpendicular to a tangent, is that angle is 90 degrees. It is sometimes, that is sometimes not realized by learners. And that is the reason why we get to this answer. Now, we received a question on this problem, which I quickly want to share with you on this question, if I remove this. The question is that, is the reflex angle at O? And this is now, I assume it is on, I don't know if it's now on this question or the previous one. I assume it's on this question. Is the reflex angle at O not subtended by the same arc with 120? And the answer is yes. If that reflex angle is twice that one. So if this is the question that you based it on, but they did that reflex angle here, that reflex angle will be twice this one, because they subtended by the same chord here. So this is 120, that one will be 240. And you can see if I add the two, I get to 360. So that one is 60 because of opposite angles of a cyclic quad, and then angle at center twice angle on circumference, this one is 120. So this 120 is not coming from this one, it comes from the reflex angle. I hope I understand your question correct, if that is the question you are referring to. Otherwise, let us know, and I will gladly clear that for you. So let's now look at the next question. Let's see if this one looks quite busy. If you look at this question, it's a beautiful drawing. Plenty of lines, circle, tangent. You can maybe see cyclic quads, all of those. But take it step by step. This one says it's called question 10 from one of our previous papers. Now, if you read, they say, in the diagram below, O is the center. Now, if O is the center, now we look for a line drawn to a chord, and there's no one drawn to a chord. We look for angle at center, twice angle on the circumference, and it doesn't look like we have that either. We look at angle in a semicircle. Can you see that's a diameter? Is there an angle in a semicircle? Yes, there is. So this angle is 90 degrees, because that is an angle in a semicircle that is 90 degrees. Now this one is already given to us as 56. If the whole thing is 90, I think you're happy that we can find this one easily. So it's 90 minus the 56, which is, I think if my mathematics is correct, I want to say it is 34 degrees. So if you add them, you get 10, and that is 8, plus the 10 is the 90 degrees. So angle in a semicircle is 90 degrees. So those are my 4 theorems on center of a circle. They told us about the diameter. I used it already. They say there's a tangent. We can look at the tangent, but before we do so, we can maybe just get used to or notice if there are any cyclic quads. And if you see that that is a cyclic quad, this DEFB is a cyclic quad. But this one, that line is not drawn here, but this one is also a cyclic quad, as you can see. Because it's this point, this and that are on the circle. Now, when I look at this cyclic quad, this last one, this is now the CBED one, can you see that we have angles in the same segment? This DC is B3, and it's this E2. So this goes to the circumference, and this goes to the circumference. This one we said is 34, so this one will also be 34. And that is because of angles in the same segment. Of course, we can say this angle will be equal to that one as well. We don't have any sizes, but we can maybe find them later. So in a cyclic quad, very important to remember, angles in the same segment. Exterior angle is not here. Opposite angle supplementary, yes. Now we think of the tangent. Tangents, the 3 theorems. Radius perpendicular to a tangent, and it's not here. Can you see there are 2 radii, and they're not drawn to the tangent. Then the tan chord theorem, and the theorem on 2 tangents not present as well. So the tan chord theorem definitely here. So if I turn my drawing so that you can look at that tangent horizontally, so we look at the tangent, we look at this angle between the tangent and a chord, the 32 one, we complete the triangle, and this will be equal to the one in the opposite segment. So this angle will be 32 degrees. And I hope you all agree with me. Can you see the angle between a tangent and a chord? If I follow, it's angle in the opposite segment of 32, 32. That's how I got that one. Is there anyone else that we can get? Yes, we can go for this triangle. We can go for that triangle. But that we have already. And if we go for this one on the side, so then it is this whole angle all the way up to here. Because this is now my chord. Tangent and chord is this whole thing. You can see 1, 2, and 3 will be equal to F. So it's quite possible to find F because we have all these angles. So we go for between the tangent and the chord. You see that is 90. This is 32. And 90 plus 32 is 122. And that will be equal to this one, 122. I want you to make sure that you can see that 122. This 1, 2, 3, that angle, the whole thing, is equal to that one if I use this triangle on the tan chord theorem. So it is this angle 1, 2, and 3 is 90 because of the angle in a semicircle. 90 plus the 32, or you can say 56 plus 34 plus 32, and you will get the same thing. You will get the 122. So I think we covered most of it. There's maybe a few more that you can find. You agree with me that this cyclic quad, we just found this one, so it's possible to find D because its opposite angles are supplementary. And that is a cyclic quad, and that 122 will give us this one, or they're in the same segment, so they will be the same. They add up to 180 with the 122. So analyze your drawing by thinking of those theorems as you do it. before you look at your questions. Now, if we look at the first question, there's a total of 3 questions for 9 marks on this one. So let's now see if we can answer that first question. They ask us to find E2. Now, E2, you will notice that I've put 34 in here. How did I get that 34? Let's just backtrack quickly how we've got the 34. The first thing we did was that we said this E2 plus 3 is 90. So we can say E2 plus E3 is equal to 90 degrees. And we say angle in semicircle. You see that 2 and 3 is 90 because this is a semicircle. That is a diameter angle in a semicircle. But E3 is 56, and that was given to us. So that means E2 is 34 degrees because they must add up to the 90. You don't need to say why because you said already why in the top. So I hope that was not too bad to find that E2. You will notice once you have this approach, most of the time when you look at your questions, you've done it already. But the important thing is that you remember how did you get to it and that you just write it down with statement and reason. Let's go to the second one, 10.2. In 10.2, they ask us to find angle EBC. So EBC is our question. So let me just move it up like this so that we have a clear view of our drawing so that we can find this angle EBC. Remember, this is what I want now. I want EBC. Let's go and have a look where it is. Angle EBC. EBC, that's what they want. Now, this one we said is 32. That one we said is 34. Now you must think, how did we get to those 2 angles? First of all, the 34 is coming from this 34, which we just did. So E2 is 34, therefore B3 is 34, and that's angles in the same segment. Remember, they're subtended by DC, the 34 and the 34. So we can start there. We can say that B3 is equal to 34 degrees, and you say angles in same segment. So that is the first part of the angle we are looking for, EBC. So EBC, I want that, is 34. Now I want to get to this 32. Where did we get the 32 from in this question? And I hope you have an answer already that you can say it out loud in your class. Where is that 32 coming from? And hopefully you will remember what we said, that this is 32, and with the tan chord theorem, that is 32. So I'm going to say B2 is 32 degrees, and that is the tan chord theorem. Everyone happy so far? So now we can say this 2 and 3, that is angle EBC. So you can say EBC is equal to 34 plus 32, and that is 66 degrees. And that is my solution for that one. All right? I hope you are happy with this solution. If I can quickly go over it one more time, they ask us for B2, B3, this EBC. This is 34, angles in the same segment, that is 34. This is 32, that is 32, and that is the tan chord theorem. And that now gives me that whole angle. Another way which you may approach this question is to say that E1 and 2 is 66, to add these two. And now to use the tan chord theorem on this triangle. So this whole angle is equal to that whole one. And then you will say the 66 is equal to the 66. So that is an alternative solution. You can decide whatever you find easiest. So you can do it separately with angles in the same segment with a tan chord theorem, and then you get it. Or you can add the two, say it's 66, and this, if you complete the triangle, circumference, angle between a tangent and a chord is equal to the angle in the opposite segment. And then you have your answer of 66 also. Let's now look at the last question. And in the last question, you will see they ask us for angle F. Now, how do we find angle F? I just want to put a piece of paper here so that I can do the solution for you. So we are at 10.3, and we are looking for angle F. Look, we've got that in there. Now, how did we get to this angle F? Now, when we start with this one, this whole thing here, we can say that E1 plus E2 plus E3 is equal to 32 plus 34 plus 56. That's one way. We can add all three of them. Or we can say 90 plus this. Or we can say this plus that, 1, 2, 3. And that answer, if I add all of these, you will get, if you add the units, it's 10 plus 2 is 12. If you add the tens, it's 6 plus 5 is 11. And that 11 is, of course, 110 now, because it's tens. Plus that 110 plus the 12 is 122 degrees. And that is where we get the 122 from. And we just added them because we know all those angles. But we know that this angle E1 plus E2 plus E3 is equal to angle F. Now, why is this E1, 2, and 3 equal to angle F? And that is the tan chord theorem. So that means angle F is 122 degrees. And that's where the 122 is coming from. So I want you to look at this carefully to say that this is my tangent. And if I go from tangent to the chord, I go to that chord, this whole angle, this is 1, 2, 3, this whole angle will be equal to the angle in the opposite segment. You can see there's the triangle. This whole angle is equal to that one. And that, if I can just show you again what I said earlier, that is the theorem that looks like this. That whole thing is equal to that one. You see, from the tangent to the chord is equal to the angle in the opposite segment. So please take note of this tan chord theorem in that form, and then you will notice it that it is here. There's my tangent. Between the tangent and the chord, it's this whole angle here, this whole thing there. This whole angle is equal to that one. So this one equal to that one. And this angle equal to that one. I add these three, 122. That one is 122. And with that, we finished this question where quite a number of theorems involve again. You will notice now on the first group of theorems on the center of a circle, we have the angle in a semicircle, which is 90, which we needed for that 34. We have two cyclic quads. We didn't use all of them, but there are two cyclic quads present here. There's a cyclic quad. As a matter of fact, there are three of them, three cyclic quads. We have a tangent, the tan chord theorem. We don't have a radius perpendicular to a tangent. But again, we have theorems from all three of the groups. And these problems, definitely problems you can expect in the exam. For around about 10 marks, you will get something like this. Make sure you can do them. But of course, you must know those three groups of theorems. Always look for them. All right, are you ready for the next one? Let's go for the next problem. There is the next drawing. And I want you to look at this closely. I'm just going to cover the question. And I want you to look at the drawing given there to you. This one also says question 8 at the top. If you have this drawing, it will be wonderful. So you can look at it. And then I want us to start reading this. The first thing you now will notice is that there, within the sketch and in the given information, there are no angles given to you. And that is where the problems become slightly more difficult than the ones we've done up to now. So I want to lift up our standard a little bit, and that we move to a problem that is slightly more difficult. And with the ones coming, it's going to, the same thing is going to happen. We're going to make them a little bit more difficult. I think with these previous ones that gave you the grounding, but now you are ready for one that maybe asks a little bit more from you. We must read this carefully so that we don't miss out on anything. When we read, they say those points are on a circle. You will see they didn't say anything about a center. There's no center given to us here. So all those 4 theorems on center of the circle is not within this, in this problem. But what they did say that these points are on the circumference. So that is a cyclic quad. But this is also a cyclic quad. You can see 1, 2, 3, 4 points. 1, 2, 3, 4 points. So we have a cyclic quad, and we have a cyclic quad there. So please take note of the cyclic quads that we have here. Something else that also shown to us is that these 2 sides are equal. Very important. So that is an isosceles triangle. But then if you go back to the given part, they say RA is this line, bisects R. So RA bisects R. So that means this line bisects this angle. They didn't tell us the size of the angle. So if you want to, you may call them both X, just to indicate that they are the same. Don't give them degrees, because then you're going to go wrong here. So you can call them X or Y or whatever, just to say that this angle is bisected. If the angle is bisected, it means it's cut into equal halves, in equal parts. So this angle is equal to that one. We don't know what they are, so maybe it's safe that we call them X. The moment you don't know, but you know they are the same, you can give them a symbol and you can work with the symbols. And that is why I said the problem is slightly more difficult, because the previous ones we have degrees and we can name those in terms of degrees. So that will be X and X. So that is now that one. Also given to us that this is equal to that, AQ and AB, we notice that. Those 2 angles will also be the same. Let's just be careful to also call them X, because if you now say they X and X, it means it's the same as that one. Just remember, we maybe can try to see if they're not maybe equal to X, or in terms of X, as we said, as we call it. And then they say those are produced. So this is all that is given to us. So we know that the opposite angles are supplementary. We know that this is 2x. So you agree that this angle, for instance, we can say it's 180 minus 2x, because that is opposite angles of a cyclic quad, because I called that x and x, so it's 2x the whole thing, and this is 180 minus 2x. So that is more or less what they're going to ask us, and we're going to most probably expect questions like, prove this equal to that, or questions like that. So let's now read the first one. They say we need to prove. We can't calculate. We need to prove. We need to prove that AQ bisects PQB. That AQ, you see that's the line AQ, bisects PQB. So they want us to prove And I'm just going to indicate here with a little cross. I'm going back to our first question. Our first question asks us that we need to prove that AQ, that line AQ, bisects PQB. So bisect. So we want to prove. What they are asking us to prove is that Q2 is equal to Q3. So you can see they phrase it extremely difficult. Instead of just asking us to prove those two angles equal, they call it like this, to say that this line bisects the angle. So if a line bisects an angle, then it means we must prove them equal. Remember there it was given to us, they are equal. Now it is not given to us. They say prove them equal. Now the moment they ask us to prove them equal, then of course we can't assume it. And now what we need to do is we need to try to find angles equal to Q2, and we want to find angles equal to Q3. And that's the best way of approaching this question. Now, where will I start? Let me start this way, and hopefully you will go with me. And I want you to look carefully and for yourself as well. Remember that one we called X. So if I look at this cyclic quad, this one down here, the AQTR one, do you agree that QR is the exterior angle because this side is extended? And this one is equal to that one. So that means I can call this also X. So what we now need to show is that this one will also be X. And once we can prove it, because that X and X is equal, once we can prove this one we know is X, if we can prove this one also X, then we solved our problem. So I'm going to say that R1 is equal to R2 is equal to X. And that was given to me, that R1 equal to R2. So I'm just saying now I'm going to call them X. And now I say that Q3 is equal to R1 and also equal to X. And that is the exterior angle of a cyclic. Exterior angle of a cyclic quad is equal to the opposite interior. That is now this Q3. You will see that one. Q3. So this angle is equal to that one. So now we have Q3. What then about Q2? Do we know anything about Q2? And I hope you can see this. If I turn the drawing, if you haven't seen it yet, I want you to look at this AP chord, this one. Can you see that R2 is subtended by this, but Q2 is also subtended by this? Look at PA, this AP or PA chord. This one subtends R2, this one subtends Q2. So we call it angles in the same segment. So what we can say in this problem now is we can say that Q2 is equal to R2 is equal to X, because R2 was also X. And the reason is angles in the same segment. Now what do you have now? We have that Q3 is X. We have now that Q2 is X. So what do you say? Q2 is equal to Q3. So that means that AQ bisects PQB. And there we've done that question for 3 marks. So they ask us to prove that they will bisect. How did we go about it? Remember, we don't have any given angles here. Given to us that they are the same, so I call them X and X. You don't need to call them X if you want to. You can just say they are the same. Then you know that Q3 is equal to R1, exterior angle of a cyclic quad. Q2 is equal to R2. And the reason for that is that they angles in the same segment. They are equal, therefore they are equal. So the X sometimes makes it easier Some people say no, they don't like it, it confused them. Then you just leave out the x, and you just say that this is equal to that given, this is equal to that with that reason. You can just leave out the x if you want to. So it's not a compulsory thing that you must prove or must use the x. Once we've got the x, we can just see which angles are the same. You agree, because of the isosceles triangle, that one will also be x. And therefore, we can find other angles maybe easier. But it's all up to you. Let's look at our second question. The second question, they ask us to prove, remember, read proof, that TR is equal to TB. TR is equal to TB. So they want us to prove these two sides equal. Now, I hope you can already see, for the reason that I use the x, you can already see this angle is x and that one is x. So they are equal, so therefore. But now you can't just say that. You must go and say, why is R1 equal to B? I called them x, so it's very easy to see. So let's look at point 2. Where do we start? We will say that Q3 is equal to R1. You can say equal to x if you want to. You can just say Q3 is equal to R1. And the reason is the exterior angle of a cyclic quad. And then you say, but Q3, let's put the angles on, Q3 is equal to angle B. Q3 is equal to B. And why is that? You say isosceles triangle, and then you say AB equal to AQ. So isosceles triangle. So the angles opposite the equal sides. Now if Q3 is equal to R1 and Q3 is equal to B, do you agree that we can say B is equal to R1? And because B is equal to R1, then we can answer the question and say TR is equal to TB. TR is equal to TB. And now the reason. And the reason is sides opposite equal angles. So I prove the two angles equal. Remember, it's not an isosceles triangle because I'm busy proving it. Those two angles are equal. And because they equal, they opposite the equal sides. So I say the two sides are equal because of that. And that is the reason you use if you prove two sides of a triangle equal. Make sure of that reason for that second part of the question. Remember the question was, prove TR equal to TB. TR equal to TB. That takes us to the last question of this one. And I want you to look at this question. They say we must prove angle P, this is angle P, equal to TRP. TRP to this one. So what they are trying to tell us is that we know, we decided already to call this angle 2x. So if we can get this one to be 2x, we prove them equal. So we want to prove this angle and that angle. We want to prove them the same. Angle P and angle TRP. So how are we going to do that? So this we already call 2x. Okay. Now we get to this. So now what we need to do is we must try to find angles equal to angle P. Can you find anyone like that? And I hope so. I'm going to turn it so that you can hopefully see it. Look at RQ as the chord. There's not a chord drawn, but imagine there's a chord. Can you see that RQ subtends angle P? You see that? But RQ subtends angle A1. A1 and angle P. So angle P to RQ, angle A1 to RQ. So what can we say first?
for this one. This is now our 8.3. I can say, to start this question, I can say that A1 and P, so angle P is equal to A1, and that is angles in the same segment. And I hope you're all happy with that. Now the big question is, what can you tell me about A1? You see there's a triangle. And this triangle is equal to this plus that. So remember I called this angle 2x. You see that is x and x. So the exterior of the triangle is equal to the sum of the opposite interior. Remember that from your early grades. So A1 is 2x. So therefore that one is 2x, that one is 2x, and you've got it. And you will see why I suggested to use the x, because it sometimes makes these proofs much easier. So how will we write it down? We will say that A1 is equal to Q3 plus B, and this will be 2x, x plus x. And the reason for that is the exterior angle of a triangle is equal to the opposite interior. But we also know that this angle, TRP, is equal to 2x. Because it was given to us that they are bisected. So this means now that angle P is 2x. So that means that angle P is equal to TRP. And that helps us to solve this problem much quicker and easier. So where did I start with this whole idea? I said because these angles were bisected, I called them x and x. Now I found that this one is equal to that one, so this will also be x. I found that this one is equal to that one, and this one is equal to that one, so I've got that one as x. This is also x because it's an isosceles triangle. This A1, this angle, this one, will be 2x because this is the exterior angle of a triangle. So that angle is equal to this plus that. Remember that theorem that says if I have a triangle, then the exterior angle is equal to the sum of the opposite interior. Okay, you can see this one is just upside down. That exterior angle is equal to this plus that. So this angle is 2x. That one is 2x, but this is equal to that. So this is also 2x. So therefore those two are equal. They're both equal to 2x. So you may give it a variable, or otherwise you may just leave out the variable. It's for you to decide. I prefer in many of these problems that we make use of a variable, and it really helps us to solve the problem a little bit quicker. I think after these questions we've done now, we've done another 3 of them. The last 3 questions are waiting for us on this, and they become slightly more difficult again. So let's now take a 10-minute break, and you stretch your legs and prepare yourself for the last few questions on the grade 11 work. I thank you. Welcome back. I hope that up to now you found this geometry not so intimidating. I also hope that you start to remember your theorems now.
The theorems, remember, from grade 11, we looked at those theorems in 3 different groups. Group number 1, on the center of a circle, 4 theorems. Group number 2, on cyclic quads. Group number 3, on tangents. Now, I want to discuss with you a few more questions on these theorems, and these questions are a little bit of a higher level than the ones that we did. So you will now see we move from questions where they gave us angles and they ask us to find other angles. We move now more to questions where they ask us to prove things. And that is where we prove sides equal, angles equal. And we're going to finish off with a question where they're going to ask us to prove a cyclic quad, for instance. So these questions, you must also be ready for them for your coming exams. We received a question from one of the learners, which I'm quite happy with. It is a question where this learner wants to know, where, in terms of the theorem that says angles in the same segment, when they're subtended by the same chord, that those angles are equal. I've made a sketch of this question that I want to discuss with you quickly before we go to our next problem. Let's look at this question. You will see there's my drawing. The learner sketched this angles in the same segment. You can see they subtended by AB. And I think all of you, if you forget about E, all of you will agree with me that this angle D and angle C are the same because they both subtended by this chord. So even if that is joined or not joined, we can say those 2 angles are equal. The reason is they subtended by the same chord or arc. Chord or arc. And I think that is where this learner asked this very, very intelligent question. And this person asked if these 2 angles, are they also equal to E? Because E is also subtended by this chord. And the answer is no, definitely not. But why? You'll remember in the beginning I said that the correct way of calling it is to say that this angle is subtended by this chord and this angle is subtended by this chord. Now this angle E is not subtended by this chord, it's subtended by that chord. And that is why it's not the same. So we say for short subtended by the same chord, but strictly speaking, that chord means that arc. So this one is not, this angle D and C is subtended by this arc, but angle E is subtended by that arc. So also how you can remember this is that when we say angles in the same segment, they must be on the same side of that chord. Or what the theorems officially say, they must be subtended by the same arc. Now this arc AB is not the same as that arc AB. And I hope that makes sense. So when you look at the chord, you have this arc AB, which subtends those 2, and that arc that subtends this one. And also another reason is, can you see that is a cyclic quad? Those angles are supplementary. They are not equal. So whatever this one is 180 minus. So the question was, are these 3 angles the same? The answer is no. Those 2 are the same. Those 2 are supplementary. The reason for it is, even this E is got that chord, this angle E is subtended by that arc, where D and C is subtended by this arc. I hope I've made this clear. It's maybe something that may confuse more students. I'm so happy about this question. Keep it up. Let's now look at our next problem. This one is called question 7. You will see at the top. Question 7. And you will see the diagram doesn't look so bad. Not so many lines. There's at least an angle given to us, which means maybe we can find some things. Depends on what they're going to ask us. But now, if you look at that, if we look at that one,
you will notice that we first need to read that so that we can see what else we have. So I cover the questions. Please develop that habit of not looking at the questions when you start a problem, and that you first look at the drawing, read through it, and see what you have. We say, in the diagram below, AC is a diameter. AC is a diameter. So that means O is the center, né? And they say it there, O is the center. Now, if O is the center, please, first of all, you need to think of your theorems, but we're going to look at the theorems now. But also remember, these are radii. Né? They're all radii. This is equal to that, is equal to that. Now, if this is a diameter, that angle is 90 degrees. It's an angle in a semicircle. Please, not this one. It must be the angle in the semicircle. That is 90. This is 33. That means we can find that one with angles of a triangle. And you agree that is not too bad. Now, also from the first theorems on center, we have a line drawn from a center to a chord. Do we know if this is perpendicular? If this is perpendicular, they will bisect. So let's have a look. There they tell us AE is perpendicular to BD. So can you see that very first theorem for the first time is now in a problem? That the line drawn from a center of a circle perpendicular to a chord will bisect the chord. I just use 3 little lines not to confuse it with this. This is equal to that, is equal to that, but this is equal to that because they're 90. A line from a center perpendicular to a chord bisect the chord. The very first theorem. Now, we also have angle at center, you will notice, and we can see angle on the circumference. So this angle is twice B1. So there's, and then we have angle at the center, and we have angle on circumference. It's A1. So this A1 will be equal to B1. But you can also say the angles in the same segment, because that's a cyclic quad. So that is another reason. Please remember, those are not equal, because they're not subtended by the same chord or arc. So we know this is equal to that, which is twice this one. This is equal to that. Which other theorems? So when we think of the first theorems, we have the theorem that says a line from a center perpendicular to a chord. We have that theorem in the problem. Second one, we have angle at center twice angle on the circumference. We have the third one, the diameter, angle in a semicircle. So we've got 3 of those theorems in here. There's no tangent one, so tangents are not present. But now about cyclic quads. So we don't have a line drawn here, but if you imagine this, we have angles in the same segment, which we already indicated. So you now already, you agree with me that we can find this angle. Because this is 90, this is 33, we can find this one. Once we've got this one, we've got that one. Once we've got that one, we've got this one, because it's angle at center. So so just keep that in mind. You can already write it in if you want to. Otherwise, you can just start thinking about it, and you can start to calculate the different angles. So let's see what they want us to find, and then we can take it from there. Just remember, this is equal to that. This we have, this is 90. Remember, that is also 90, né? And this one we can find from this one. So that means we can work out these angles. I also want just to show you one last little thing. Maybe some of you picked it up. If I turn it around and I look at chord AB, will you agree with me that that angle and that angle will be the same? They both subtended by AB on the same side. So 33 is the same as D1, angles in the same segment. So this 33, that one will also be 33 degrees. Because of angles in the same segment, those will also be equal. So I think we know more or less what is going on here. By the way, we can still write that one down if you want to, because 33, what must this one be? Because they must add up to 90, because this one is 90. And I think 90 minus 33 sounds to me like 57, which is 7 and the 3 is 10, 5 and 3 is 8, plus the 10 is 90. So you hopefully agree with me that is also 57. So I just wrote that in, so it maybe makes it easier for us. Let's now look at the first question. They say C is 33. Now we used that 33 already. They say find A1. Now A1, I just wrote it in, is 57. Why is it 57? So let's just write this down. So where will we start? You will see it's a 3-mark question. We will start with the fact that this angle is 90 degrees. And this is 33, and therefore that will be 57. So I will say here, they ask us for A1. So I think the best is maybe not to use these. A shorter route will go to this one and then to find A1 straight away, instead of going to this one first. So we can say here that D1 is 33 degrees, and that is angles in the same segment. And now we know that E1 is equal to 90 degrees, that E1, and that was given to us that the lines are perpendicular. You remember at the top there, they say it's perpendicular. So now we can find A1 is then equal to 57 degrees, and that is angles of triangle equal to 180 degrees. And there we've done it. We found the A1, so you can go either finding this one and then say angles in the same segment to A1, or you can find this one from the same segment and then say angles of a triangle. Whatever way, you will agree that was quite easy. The second problem is D2. They want us to find D2. Now, how do we find D2? Let's look where D2 is. D1, there is D2. How do we find that angle? And I want you to think with me about this. How will we get to that angle? And now it is very important that this is number 7.2, 7.2, and we are looking for D angle D2. I'm just going to write it down so that we remember which one we are looking for. Now we want that one. Do we know D1? Do we know the whole thing? If we can find the whole angle D1 and 2, subtract, we get to D2. And this is why it's so important that you remember the radii. Can you see those two sides are equal? Because it's radii. That is an isosceles triangle. That is 57. What is this whole thing? So you can say that D1 plus D2 is equal to 57 degrees. And why do you say it? You say that OD is equal to OA. It's a radii, isosceles triangle. Because that one we've done just now. So now we know that is it. So now you can say, therefore, D2 is then 57 minus 33. And your D2 is then, if you subtract, 7 minus 3 is 4. 5 minus 3 is 2, and that gives me an answer of 24 degrees. And you agree with me, it's quite easy, but it's very easy to miss this one as well. And many students miss these because they don't think of the isosceles triangle, the radii. And that is what you needed to remember in this question. All right, let's now look at the last one here. They say show that AE, and I'm just going to drop it so that you can read it with me. Show that AE bisect DAB. So, in short, what they ask us in this 7.3, not 8, but 7.3 question, they ask us to prove that A1 is equal to A2. That is what they want us to show. That A1 is equal to A2. They ask us that AE bisect DAB. Can you see there's the question? AE bisect DAB. Now, DAB is that whole angle must be bisected. Now, to do this, it's not too difficult. We already know that A1 is 57 degrees, and that's already proven. So we're not going to say again. You may say also why, but it's not necessary. So we must now find A2. The important thing is angle B is 90 and this is 33. So if you work with a big triangle, you will hopefully agree with me that you can find that. So we're going to say that angle B is 90 degrees, and that is an angle in a semicircle. So that means angle A2 is 180 subtract 90 plus 33. This is 90. This is 90, this is 33, 57. This is 90, this is 33. So that will be 57. But if you do that calculation, what will you find? That A2 is 57. And this is angles of a triangle is equal to 180 degrees. So therefore, A1 is equal to A2 because they are both equal to 57. You may say it there as well if you want to. It's not necessary, but you may do that. And then, maybe to be quite clear, tell them what you did when you proved this equal. You showed that. So you can say, therefore, AE bisects DAB. And that is what we proved. To bisect, those two angles must be equal. And I just want you to look at that for a moment and see exactly if you're happy with what I've done. They ask us that if AE bisect the angle, that means if A1 is equal to A2. A1 is 57. We've done that already. This is a triangle. That angle B is 90 degrees because it's an angle in a semicircle. 33 was given to us. So that is 57. So those two angles are equal. So that angle A is bisected. And I think you agree with me. This problem, after our break, not too bad. So let's go to one that hopefully is a little bit more of a challenge. But the more you do these, you will realize that they become easier. And it's not that the problems are always easier. It's the fact that you remember your theorems and you manage to recognize them in your drawings. And that's the important thing. That is why it's so important you must remember those theorems. Remember the three groups that I told you about. Let's go for the next one. Okay, this one is called 8.2, this problem. And there are 4 questions that we need to answer on this one. You will notice that there's quite a bit of lines again. You can see if before we read anything, you most probably will be able to see that we expect to be a tangent. There's a circle, there's a center, there's an angle in a semicircle. It doesn't look like there's angles in the same segment. It looks to me like there is a cyclic quad that we can use. Remember, you go outside of it. And so yes, let's read and let's see what we can find, which theorems are present here. They say RS is a diameter of circle with center O. So this is a diameter, and this angle will be 90 degrees. All right. If you go to P, you can see there's not a line, so you can't say anything about that one. So this angle, 90 degrees, because this is a diameter. Center O. Anything else? Do we have a line drawn from the center? No. Do we have angle at the center twice angle on circumference? And it doesn't look like it. We have angle in a semicircle. Do we have a radius and a tangent? And they tell us later that this is a tangent. So you will agree with me that will also be 90 degrees. Because a radius is always perpendicular to a tangent. So if that is a tangent and that comes from the center, And that is why it's so important that you remember that theorem. So that angle is 90 degrees here. 90 degrees. So remember that little block. Little square that indicates 90 degrees. Then what else is given to us? They say this is produced. So let's just, before we carry on with this, let's just quickly have a look and see if we can find any cyclic quartz. Because many times they don't tell us that they are cyclic quartz. But you can see SRPT is a cyclic quartz. So if I look at the chord TS at this arc, can you see that I get R2 and I get P1? So this angle is equal to that one. I'm going to put little black dots in them to indicate that they are equal. They're in the same segment. Is there anything else that you notice? And yes, if you look upside down at chord PR, you can see you go to angle T2 and you go to angle S1. So this angle, if I put a little cross in it, will be equal to that one. So this will be equal to that, angles in the same segment. This will be equal to that, angles in the same segment. And then they say there's a tangent. And then they also tell us that R1 is 50. So they say this R1 is 50 degrees. Now, because this is 90, you will agree with me, R2 will be 40 degrees because they must add up to the 90. And this is equal to that, so that is also 40. I'm not going to write it in because it's going to look a little bit messy. So that one we know will also be 40. Just keep it in mind, we indicated that. So we have a few angles. But now, if you allow me to turn this drawing around so that the tangent is horizontal, this is a tangent, a radius is perpendicular to a tangent, that one we use. There are not two tangents drawn. So if I look at this one, I look for the tangent and I look for a chord. And this is equal to the angle in the opposite segment. This one, which indicated here with this little arrow, which is 50, will be the same as that one over there. So this one will be the same as that one. And this, I'm just going to turn it this way so you can read. So this will also be 50 degrees. That was 50, opposite segment, that will be 50. And you will see between the tangent, that is the only chord that completes a triangle. So we have that one as 50. Now you will agree, if this one is 50, 90, that one is 40, so we have those angles. We don't have them individually here. Number 1 and 2, we know this one is equal to that one. We know this one is 90, etc. So I don't know if there's anything else that you can find. You may look at the possibility of an exterior angle of the cyclic quad, but it doesn't if I complete the cyclic quad, but there's not a chord drawn there, I have an exterior angle here, the T3, which will be equal to, but we don't have an angle there because it's not drawn. So we can't use that. There's no any one of the other sides extended of the cyclic quad. So I think we've got most of it that we need. So let's get going on it and let's see if we can answer the questions with our information now. So what is the first one? The first question is, find the size of angle WRS, and it's 90 degrees. So extremely easy. You're going to say just that WRS is equal to 90 degrees, and your reason is radius perpendicular to tangent, because they always, if there's a radius and there's a tangent, they are always perpendicular. And that was all. You can see it's a 1-mark question. You just write down the answer. There was no calculations required. Now they ask for W, that angle. Now, I know if you look at this, you will agree with me, it's very easy to find W, because if I go for the big triangle, I know that is 90, I know this is 50, so that one must be 40. But how do we get it? The 90, we just proved it. The 50, where is that coming from? It's coming from the tan chord theorem. So where we need to start. So in this 8.2.2, we're going to say that angle S1 plus 2 is equal to 50 degrees. And that is my tan chord theorem. And now you say angle W is equal to 40 degrees. And that is the angles of a triangle equal to 180. Because we already said that is 90. We told them that this is 50. So therefore, that will be 40. You may say more if you want to on this one, but it's not really necessary. The 2 steps for the 2 marks are quite suitable. Let's now look at number 3. In number 3, they ask us for P1, to find P1. So if I just move my sheet a little bit up, and I'm going to say that this is 8.2.3 that I'm going to do. And in this one, they ask us to find angle P1. So I'm just going to write it down here that we want to know what P1 is. So let's go to this angle P, what they are talking about. They want angle P1. You can see there's a black dot, and there's a black dot. It means they're equal. We already said that is 40, so P1 will be 40. How do we write it down? We start with this R2. We say R2 is equal to 40 degrees. Remember that 50 was given to us. So the reason is radius perpendicular to a tangent. That is tangent. So that is 50. That one will be 40 because they are 90 degrees. And now we say P1 will be 40 degrees. So this R2 is 40. P1 will be 40. And what is the reason for this? And that is angles in the same segment. Because they both subtended by ST. Subtended by ST. This arc ST. So there's the one, and there's the other one. This is equal to that. And there we are finished with this question. So, what is the last one? In the last one, they ask us to prove that V1 is that one. Just going to write it down, 8.2.4. They ask us to prove V1 equal to PTS. V1 equal to PTS. So let's have a look at that question. We want to prove V1 equal to PTS. PTS. So that is T1 and 2. So this PTS, just for us to know, otherwise we need every time need to look, they talk about T1 plus 2. So T1 and T2. So they want us to prove V1 equal to T1 plus T2 in this fourth problem. Now, is there anything you can tell me about these angles? You will remember that we just calculated this W as 40. Now, if W is 40, and we already worked out P1 to be 40, and now you need to watch closely, because this solution is not as straightforward. I want you to look at this drawing, at this quad. There's not a circle around it, it's just a quad. You can see this W, V, P, T, this one. That side is extended. That angle is 40 because of angles in the same segment. That one was 40 because of angles of a triangle. We've done it already. So I can say that P1 is equal to W, is equal to 40 degrees. And that is proven. that is proven to us. Or we've done it already. Not to us, but we've done it. So we know that this angle is equal to that one. Now, there's something very important that you need to understand. The moment that we have a cyclic quad, not a cyclic quad, a quad, where this angle is equal to that, then this is a cyclic. So that is what we're going to use now. Because there was not a circle around it, we don't know that it is a cyclic quad. But if we can prove the exterior angle equal to the opposite interior, or we know it, and we know that this is equal to that. You see that side is extended. So this angle 40, that angle 40. So we know those angles are equal. They're both 40. What do we say about that quad? We can now say that this PVWT is a cyclic quad. And what is the reason? Exactly what we just did. Exterior angle equal to the opposite interior. And that is why this is a cyclic quad. So now this is quite important. So this quad is a cyclic quad. Now why is this important to us? Because if this is a cyclic quad, we are looking for T1 and 2 to be equal to V1. But do you agree that then will be true? And I want you to look at this closely. So we can now say that this angle PTS, this is T1 and 2, will be equal to V1. So this angle will be equal to V1. And the reason is now exterior angle of a cyclic quad. So what you need to understand of what was happening here, because of what we've done already, we proved, or we showed, or calculated, that P1 is 40. We calculated W, that is 40. If I can just move the drawing down. So P1 is 40, W is 40. But this is the exterior angle. You can see that side is extended of this quad. So the moment that this is equal to that, this is not just any quad, this is a cyclic quad. And because it's a cyclic quad, this exterior angle, which is number 1 and 2, you can see there's the cyclic quad, this is the exterior angle, is equal to the opposite interior, is equal to V1. And that is what they ask us. And then we proved it. So to get to this answer, the challenge was to first of all realize, because of the previous two questions, we've got now a quad that is a cyclic. And because it's a cyclic, we can prove this. And I hope you understand this reasoning. It's slightly difficult, but once you think about it and think carefully, I'm sure you will be able to master this. So they basically, by asking us these questions, they sort of helped us already to cope with this question. You will see this last question was for 4 marks. So it is not an easy question because it's not just a 1 or a 2 mark question. So you will see it's 4 marks here. So what did they want us to notice? That this W and P1, so this W and P1, we calculated both of them, both are 40. And this is the exterior angle. And because they are equal, that is a cyclic quad. And because it's a cyclic quad, this exterior angle is equal to the opposite interior. And with that, we finished this question. I hope you are still with me. Can we do a last one on the grade 11 work? I left this question for last for the simple reason that it's not necessarily extremely difficult, but it's slightly different in the sense that they don't give us angles. They just gave us one angle that is x. And you will see that is the Q1. They call it x. So there are no degrees given. And they sometimes like this. And this can become a little bit more difficult if you don't make sure to understand this. All right. Let's read this question. In the diagram below,
O is the center of the circle. Now, when we read that, please remember to think of the 4 theorems. Center of a circle. Is there the line drawn from the center perpendicular to a chord? No. Is there an angle at the center, twice angle on the circumference? And yes, I can see one. But be careful with this, ne? I almost took this one. It's not correct. Can you see that this looks like an angle at the center, but T is not on the circumference? So if you look at this one, we can maybe consider RQ. You see that goes to O, and that goes to P1. So O1, this O1 will be twice P1. So if you look at it at RQ, angle at center, angle on the circumference. This angle twice that one. So that is quite clear for us to see that this is equal, that this is twice this one. Please, this one you can't use because this T is not on the circumference. It's quite clear that there's a cyclic quad, but let's look at the other theorems. There's no diameter, there's no tangent, so those theorems are not part of it. They say those are the points on the circumference, so that is a cyclic quad. There are no exterior angles. We know the opposite angles are supplementary. And if there are angles in the same segment, you can see that one is not drawn to the point on the circumference. So we don't really have, we can see this maybe. If you look at PS, no, it doesn't work because this T is not joined here. So we can't look at that one and this one. So we don't really have any angles in the same segment. So what they do tell us as well is that this side is equal to that one. So that means this angle is equal to that one there. So remember, isosceles triangle, this one. That one is X. Is there any other angle that you can find that is also X or in terms of X? If you just think about it, remember the one thing that I said that we always tend to forget, and that is radii. Do you agree with me that this will be the same as that? Because it's radii, so there's an isosceles triangle. So if this one is X, that one will be X. And if I look for O1, this O1, I'm just going to draw a little arrow to this side. What is O1? Can you see that's angles of a triangle? It will be 180 minus 2x, because this is x and that one is x, because I just need to use 3 little lines here, because otherwise you get confused with those. So this is equal to that. That is an isosceles triangle. That is x given. This is x. So angles of triangle, this is 180 minus 2x, x plus x. Angle at center, twice angle on the circumference. So what is this P1? If that is 180 minus 2x, this is 90 minus x. And so we can find angles in terms of x. And we expect questions like that. So let's look at the first question and see if we are on the right track here. So they say, calculate with reasons P1 in terms of x. P1 in terms of x. You can see, and I wrote it down already. So let's just do it. 8.2.1. They want P1 in terms of x. Where do we start? We must find this one. How do you get this one? We must get this one. So we will say R1 is equal to x. And that is because OR is equal to OQ, and that is radii. Now we say O1 is equal to 180 minus 2x. That one is 180 minus 2x, and the reason for this is angles of a triangle is equal to 180 degrees. Because this is 180, subtract the x plus the x. Now we say P1 is 90 minus x, and that is angle at center
is equal to 2 times angle on the circumference. And there we did this P1, which you will agree more difficult than the ones where we have degrees given to us, angles given to us. Now we work in terms of x. So that x was given, that is x because of the radii. Angle at center twice angle on the circumference, we can get to P1. All right. Now they at this one again where they say show that TQ bisect an angle. Which angle must be bisected? TQ, you see it's that line, bisects PQR. So they want us to prove that in this number 8.2.2, they want us to prove that Q1 is equal to Q2. This is what they want us to show. Remember, it's not equal. I said the question mark. That is my question. So we must prove them equal. To prove them equal, this one is x. We must get that one x as well. So how will we find Q2? Because we know already that Q1 is x. So how do we prove Q2 to be x? So what you can say to start this question always, because they say the line must bisect, you can say, prove this equal to that. That is what your intentions are, to do that proof. Now, how will we do it? Where will we start? We know that this angle is 90 minus x. You must remember that. All right? So what else will be 90 minus x? And what you need to look for is look at that. So those two sides are equal. So that means this is an isosceles triangle. So do you agree with me? This angle at R, 1 and 2, both of them together. So we can call it QRP if you want to. That QRP is equal to 90 minus x. And the reason for this is isosceles triangle, and then we say QP equal to QR given. So this angle 1 and 2 is 90 minus x, because it's the same as that one. Okay, we have that already. Now the question is, if this is 90 minus x and that is 90 minus x, what is that angle? So we work with angles of a triangle. So what we will do is, we will say angle Q plus P1 plus R1 and 2, P1, we can say Q1 and 2, that they know exactly which ones we are talking about. So that angle plus that one is 180 degrees. And that is angles of a triangle equal to 180. I just want to move it up a little bit. Now, which ones do we have? Q1 and 2 is what we are looking for. So this Q1 and 2, we want to find that. Plus P1 is 90 minus x. Plus R1 and 2 is 90 minus x is equal to 180. So it's just a substitution. Now 90 is 180. Take it across, it cancels that 180. Minus x, minus 2x, take it across. So are you happy that angle Q1 and 2 is 2x? So this angle is 2x. But 1 is x, so what is Q2? That means Q2 is x. And you can give the reason that Q1 is equal to x given, if you want to. So therefore, that one must be x. So that means now that Q1 is equal to Q2. So we proved those two angles equal. What was the question? The question was to prove them equal, but the way they've put it, and you notice now we've done a couple of these questions, they said TQ bisect the angle. Now for TQ to bisect the angle, it means we must prove them equal. So what do? We know this one is 90 minus x. The angle is isosceles, so that is 90 minus x. You add the 2, subtract from 180. That is 2x. This one is x, so therefore that one is x. That means they are equal. So, I hope this question was not as terrifying that you think so far. We've got still one last one to do, and that is the third one here, which you will see at the bottom where they say, show that STOR. Now have a look where this is. STOR, this. Show that that is a cyclic quad. Now, how do we show that is a cyclic quad? How do we prove a cyclic quad? So before we discuss this, I just quickly want to discuss this with you on how to show that something is a cyclic quad. The one way we showed already, and this is one that is very common in exam papers. We work with the exterior angle equal to the opposite interior. If this is equal to that, it is a cyclic quad. All right, so you can have any exterior angle. So when we go back to this one, do we have an exterior angle of this quad? It's not a cyclic quad yet. Remember, we are looking at this quad. STOR, this quad here. If you look at those where my fingers are, that quad. Do you agree with me? This angle, O1, is an exterior angle. We can't say this is equal to that because we don't know it's a cyclic quad. We must now go and find angle S. And if we can find angle S to be also 180 minus 2x, then those angles are equal. Then it means it is a cyclic quad. So always remember, we are busy with the opposite. If they say it is a cyclic quad, then of course we can assume the angles are equal. If they say prove it a cyclic quad, we must show the angles are equal. Then we can say it is a cyclic quad. So what will we do? We're going to start with the previous one we just did. Remember, that is x, and that one is also x. So do you agree this whole angle is 2x? That is a cyclic quad, the big one. So what is this angle S? And I hope you agree with me, it's 180 minus 2x. Because that is 2x, this is 180 minus 2x because they're supplementary. Because that is a cyclic quad. Can you see this angle S is 180 minus 2x? O1 is 180 minus 2x, but this is the exterior angle equal to the opposite interior. Therefore, that will be a cyclic quad, and then we proved our problem. Let's just write this down so that you look at it one more time. So in this question 8.2.3, the last one, we have that Q1 plus Q2 is equal to 2x, and that was already proven. Then we say angle S is 180 minus 2x, and that is opposite angles of a cyclic. So this is 2x, this is 180 minus 2x. Now, remember, this O1 we put here, but we never said that why O1 is this. We know this one, that one we found. So we now say that O1 is twice 90 minus x. It's twice this one. This one is twice that, which is 180 minus 2x. And that is angle at center is equal to 2 times the angle on the circumference. So as you now can see that we've got, sorry, this is not Q, this is O. I've made a mistake here. Just change this. This is O1. O1. So we have O1 equal to 180 minus 2x. That one. Angle at center twice angle on the circumference. We have S is that. So this means that STOR is a cyclic quad. And why can we say it? Remember, that's what they ask us, STOR. Why is this a cyclic quad? And the reason is O1 is equal to S. And what does this mean? That is the exterior angle equal to the opposite interior. Because we proved those two angles equal. O1 and S. O1 and S. And this and that angle are the same. And this is the exterior angle equal to the opposite interior. So therefore, that is a cyclic quad. So please remember, when you want to prove a cyclic quad, you always try for this exterior angle to be equal to the opposite interior. Before we finish off with these questions, I just quickly want to take you back to one of our previous questions. Sorry for the delay. There was a question from one of the learners, and if I'm not mistaken, it is this question. The learner was asking that if I can explain the last two questions again, the 7.2 and the 7.3. I hope I've got the correct question. That is question 7, and they ask for 7.2 and 7.3. Let's just go over this quickly, and let's just do it one more time. Please just read again. Remember, AC was a diameter, so that angle is 90 degrees. That we know. Center of a circle, a line drawn from the center perpendicular to a chord will bisect the chord. Angle at center twice the angle on the circumference that we have. We have this angle equal to that because they are angles in the same segment. And we have those lines that 90 degrees. We have the 33 here. If this is 33, that will be 33. Okay, and if we get to that 33, what do we do? Angles in the same segment, and that 33, that will give us that answer. This one is 90, we know, but what we also know of this one is that if this is 90 and this is 33, we can find A1, and that was the first question. So that was angles of a triangle. So how did we get to question 1 here? 33 given, that is 33, angles in the same segment. Given to us, they're perpendicular, so this is 90. Angles of triangle, that is 57. If that is 57, that is 57. And then, well, we don't know if we need it, but they are angles in the same segment. So number 1, we're happy with it. That A1 is 57, reason it, angles in the same segment, 33, 90, angles of a triangle. How do we get to D2? D2 to this angle. All right, that was one of the questions. The first thing is, what is D1 plus D2? And I want you to think with me. And that is the one that I said many times people will miss. Can you see that I've got 3 lines in there? All right. And no, that was only 2 lines. But this one, let's make it 4. And this one, 4. That is an isosceles triangle. This one. So this angle, which is 57, this angle here will also be, this will be equal to that. Because that is isosceles. Because this side is equal to that side. Those two angles are equal. So that means D1 and 2 is 57. So what is D2? 57 minus the 33, because that part is 33. And that gives us the D2. So this D2 will be equal to 24 degrees. So this one is 24 degrees. We've got it from angles opposite equal radii. That's the radius, that is the radius. 57, this is 57. 33, that will be 24 because they must add up to 57. Now they ask us to show that AE bisects DAB. So they basically ask us to prove that A1 is equal to A2. This is what they ask us to prove. So how will we get A1 equal to A2? We know A1 is 57. How do we find A2? Okay, you go for the big triangle, ABC, 33, B is 90. What is that? A2 is 57. So all that you say is, you say A1 is 57, and that is given to us. Or not given, proven rather. We've proved that already, proven. Now we say angle B is 90 degrees, and that's angle in a semicircle. Angle in a semicircle. C is equal to 33. That was given to us. 33, 90, angle in a semicircle. So A1 is 57. So what is A2? A2 is 57 angles of a triangle equal to 180. And there we proved A1 equal to A2. And that was the 7.3. So I hope the person who sent in this question that you are happy with it. To get to D2, you need to remember the radii. Isosceles triangle, 57, 57, that is 33. You just subtract. And then for the bisect, it means A1 equal to A2. We know A1 is 57. You must just find A2. This is 90. This is 33. Angles of a triangle, that will be 57. Therefore, they equal. All right. This brings us to the end of our grade 11 problems. You will find from your teacher more problems that we've sent to your school. Please try some of them on your own. Ask your teacher to help you. Please remember these theorems, the three groups. We're going to take a break now for 10 minutes. And when we come back, we will move to the grade 12 geometry. Now, I know that you haven't done this geometry yet. This is for term 3. I just want to do an introduction for you so that when you start school after your holidays, that this geometry is not too frightening for you. So, enjoy your little break of 10 minutes. I see you after that. Welcome back. We're now going to discuss grade 12 geometry. I know you haven't done this at school yet. It's only for term 3. But this will really help you to get going on this grade 12 geometry. So when you return to school and your teacher discuss this with you, you have a little bit of a background already. I am not going to go in depth into very complicated problems. I want to explain principles to you that you will need. And to understand this, grade 12 geometry, the first part, I'm going to divide it into 2 sections. That's why I refer to the first part. Is that we're going to look at 2 theorems specifically that is always tested in grade 12. And the first part is on the first theorem, which is on proportions.
And the second part is on similarity. Now, these words may be new to you, but we are going to look at triangles where the sides are divided in equal proportions or the same proportions. And then the second part is we're going to prove two triangles similar. But let's first focus on the first part. So for us to be able to look at these proportions or ratios, we need to go back to our earlier grades and just maybe recap quickly on a few important things on how to divide a line segment in a ratio. Now, I prepared a few PowerPoint slides for you, which I want to discuss with you to explain just this basic principle. And this is our background that we need to cope with this very first theorem. And then we will look at the theorem, and then we will discuss a few problems. So let's look at this few slides. And as we go through them, I will take it very slowly so that you stay with me and understand what I'm trying to explain to you. So let's see how you cope with this. So I'm going to quickly discuss ratios with you, as you can see now on your screen. So if we have a line AB, and there's a point C on this line, then you can see that is the line AB, and this line's got a length of 21 centimeters. So please take note, the whole length of this line AB is 21. Now, I want you to divide this line in a ratio of AC to CB, and you remember this is how we write down a ratio, AC to CB, in the ratio of 4 to 3. It doesn't mean AC is 4 centimeters and CB is 3. That is where many people go wrong. Because you will see, if you do that, they will add up to 7, and the line is 21. So of that 21 centimeters of line AB, AC is 4 parts of it. And that you will see if you look at AC, I divided that in 4 parts. And CB is 3 parts of the 21. Now, how do we calculate this in an easy way? What we do is, there is your AC, which is now 4 parts. You see, I wrote it in there for you, 4 parts. CB, and that is 3 parts. And that comes from the ratio of 4 to 3. That the AC is 4 of the parts, and CB 3 parts. Now, that is the same slide again. Now what we do is, what I told you already, AB is not 7 centimeters. Remember, AB is 21. It's not 4 plus 3. It's 4 parts and 3 parts. Now, how will we work out the length of both those pieces, the AC and the CB? We use a variable, but don't use X and Y, because that's our algebraic variables. We use a variable like K or P. It's always nice to use. And we say every part is K. And you will see I've put the K in every part. So let's call every part to be K. So now you will agree, if you count AC, how many Ks are there? There's, of course, 4 parts. So AC is now 4K. And what is your CB? That is 3K. Now your question is, what is then the AB distance? The 4K plus the 3K, if I add them, gives me the 21, which was given to me. And do you agree? Now we can solve for K. So 7K is 21, so K is equal to 3. So every part is 3 centimeters. Now what is the question? The question is to find AC and CB. So they are the 3 centimeters now written into every part. That was K. So what is the AC? It's the 4K, or 4 times 3, which is 12. What is CB? It is 3 times 3, which is 9. And then your ratio of AC to CB, and it can also be written in a fraction form, is AC over CB. We can write it as 12 over 9 or 4 over 3. Now, this little section, what this is all about is just to show you a revision of what you've done in your earlier years on how to divide a line into a specific or a given ratio. You're going to need this for our first problems. And you will see when we start doing problems that I'm going to use this again. So I just want you, this will not be given to you in an exam like this, but it will be part of the grade 12 geometry. But if you can't do it, you will struggle with your grade 12 geometry. So it's very, very important that you look at these few slides and that you know how to divide a line of 21 centimeters in a given ratio. So what we're now going to look at is triangles. And you will now see a triangle on the screen which is called ABC, the big triangle ABC. On the side of AB, there's a line drawn, a point D, and the line is drawn to point E to the other side. Now, what this theorem tells us, if those two sides, that's now DE and BC, if they are parallel, then the sides are proportional. So that means AD over DB will be equal to AE over EC. So that means we can write that down. Now that is what the first theorem tells you. If those lines, that line drawn between the two sides of a triangle, if that line is parallel to the third side, then that line divides the two sides into equal proportions or the same proportions. So that means, as you can see now, that AD over DB is equal to AE over EC. But that's not the only way we can write down the ratio. So you must now be very careful and see, because we sometimes need to change the ratios. So in what other way can we still write this ratio? So if those lines are parallel, we can write it like that one, or we can write it like this. Now, how are they different? We have now AB, can you see the total side, over AD, which is the top part. And that is equal to AC over AE. Now, what you need to know about this and understand, in the first ratio, you will see it was the top part over the bottom, and then on the other side, the top over the bottom. When we look at the second one, it is the total side over the top one, and then AC, the total side, over the top one, AE. So what do you think? We can now also say total over the bottom one. So there are more ways to do it. So I go the total side, AB, over DB. Then I say it's equal to the total side, AC, over EC. And I want you to compare these different ones. In the first one was the top over the bottom, equal to the top over the bottom. Then I took the total side over the top part, total over the top. Then I took the total side over the bottom, total side over the bottom. Any other way we can write these ratios? And look at this one. I can take the bottom one, the DB one, over DA. So the bottom over the top. And then you must do the same with the other one. So you must always work with corresponding ones. So if you wrote DB first, the bottom part, then you must write EC or CE first, or at the top on the next one, and then EA. So we can say DB, so you read it down not from A, but from the base angles you read it down. DB over DA is equal to CE over EA. Instead of reading it from A, we read it from B and C. Another way of doing it is again to go for BD, the bottom one, but reading it from B.
over BA. So now I go over the total length again. And then I say CE, the bottom one, over CA, the total one again. So as you can see, these ratios, you may write it depending on what is given to you. You will see when we start with the example. So I just want you to take note of it now, that these ratios can be written in different ways. There's not only one specific way on how to write down these ratios. There are different ways, and that is what I want you to see within this drawing of a triangle. How do we write, and what are all the possibilities of writing down ratios? When we do a problem on this, they're going to give you a triangle. They will show you which sides are parallel. And they will maybe give you a side, they will give you a proportion, and they will ask you to find another side. And then we're going to use that first stuff where we use the K. We're going to bring that in, and we're going to write down one of these ratios or proportions. So just be aware that these proportions, you can do it in different ways. So let's move on. I have an example here for you on the screen. There is a triangle given to you. And as you can see, there are three sides that is parallel. Now, if you think of this now, and you work with the big triangle, the DAG one, then you can take either the CE or the BF, which is parallel to the AG, and you can write down proportions using whatever parallel side, and you can say those sides will be proportional like we just did. So let's see what they ask us. I'm now asking you, if I say BC over CD, what will that be equal to? And you must now see which triangle I'm using. I'm using that BCD line. So I'm not going to A and G. So BC over CD, follow your parallel lines, will be equal to, what goes to the top? The one that corresponds with BC, and that is, write it down, and that is FE. The one that corresponds with CD, and that is ED. So you're supposed to get that. FE over ED. If I ask you for this ratio, so you can see in the previous one, I just gave you examples. Now I've got a specific example with parallel lines, different ones, and now I give you a ratio, and I ask you, this ratio is equal to what? So now we have BD at the top over CD. Can you see it's like the total length over the bottom one, CD. So we will go to the other side. Which one corresponds with BD? And that is FD. Which one corresponds with CD? And that is ED. And we write that down. And I hope you start getting this. It depends on what we need. We're going to write down these ratios. From what is required, what is the question, and what was given to me will tell us which ratio to use. All right, there's the triangle again. Now I just put it in, we can put ratios in a fraction form, or we can write it like that. AB2, we read it as AB2 BD. Now what is AB2 BD? So can you see I now work with the parallel side of BF and not the CE one. So I work with a big triangle, and I work with AB to BD. So what will it be equal to? To GF to FD. And I hope you've got that answer. So AB to BD is the same as GF to FD. And remember, you can write it as a fraction or as AB to BD. It means the same thing. There's another one. I say AD, the total distance, over BD or 2BD. Then I need to take the total distance, GD, to, and which one corresponds with the BD, and that is FD. and you will get that. So, I hope this is not too frightening. Very straightforward. How do you find these? You always look at your lines that's parallel, which ones are given, which ones they want, and from that you will write down your proportions. So, let's look at our second example here. These are very straightforward, just to explain to you all these basics, because you haven't done this topic yet. So I just want you to see what exactly happens, that you get a feel for this proportionality. Right, we've got a triangle ABC, we've got a line DE drawn. They now tell us that AB is 28 millimeters. They give us the length of that side. What else? You see there, I've put the length in, 28. Always put it onto that side so that you remember that side is so many millimeters. Then they told us that those two sides are parallel, DE and BC. So I'm just putting that in for you on the drawing, that they are parallel. Now the theorem says if those lines are parallel, the sides are proportional. Now we've got the total side we have here. Now what do we still need to know what they want from us. So let's just see what else is given to us. Also given to us is that AE to EC has got a ratio of 4:3. Now you remember that very first problem on the line that I did with you. When we work with that ratio, we're going to call it parts, or we call it K. So AE, I'm going to call it 4K, or 4 parts. And EC is going to be 3 parts. So let's just put that in. You see the 4K and the 3K. That comes from the ratio given to you. So that side is divided in that ratio. So we now know that AE over EC is equal to AD over DB. But on AD and DB, we don't have the respective sides. We've only got the total one. So on this other side, you agree we can get the total one, because that will be 7K. And that is what I'm just showing you now. What is that total length? Because I want them to correspond with the other side. That total distance is 7K. So now I've got the total distance, 7K. On the right-hand side, I've got the total. I've got both parts here, but they still didn't tell us what they want from us. So let's just have a look. They want BD, so the bottom one. And you can see, I just put the question mark there so that you can see which one we are looking for. So now we need to write a ratio. Now, how does this work if you write a ratio? You always start with the part that you want. So as you can see, BD is the one I'm looking for, over the side given to you, and that is AB. And then you go, it's equal to, and then you go to the other side, and you put the same ratio down. So if you say DB over AB will be equal to EC over AC, and I just make some space for this. Now I just indicated to you, that is the one that I want. I marked it in red. That is the one that I always put down first, over the one that I have, the 28. And now I find the ratio, the similar ratio on the other side. And that will be the 3K one over, and I'm sure you said AC. So now you can see exactly with this color, red and blue, you can clearly see how I'm going to write down my ratio. Where do I start? With the one that I want, BD, over the one given to me, the AD, the AB. Then the red one again, 3K over the 7K, the AC. So let's write it down. So I say BD is what I want, over the 28, is equal to the 3K, the EC, over the total, which is 7K. You agree those K's will cancel. We multiply, and I'm just going to do the calculation now. We multiply we first cancel the k's, we multiply by 28, and your answer for BD is 12 millimeters. Now, I am sure you didn't find this very difficult. So always remember, you look at your parallel sides. That tells you which sides are proportional. If there are sides given to you, physical lengths, you put them in. If there are ratios given to you, you put them in terms of K or a P, and then you go for the side that I want over the side that I've got is equal to the other ratio. So let's do another example. You will see now this becomes a little bit more difficult. There's now more than one triangle here. There are now two sides parallel, but those parallel sides you can find within different triangles. Either in CDK, you will see there's two sides parallel, and we can look at different triangles here. But let's first see, before we continue, what is given to me. First of all, there's a ratio. AD to DB is a ratio of 2 to 3. So then there's a second ratio given to you. A BE over EC. So if you look at that triangle is sort of on its side. It's triangle ABE. You can see the two sides are parallel in ABE. So I have the AD over DB, and I have the BE over EC. And that is a ratio of 4 to 3. The ratio they ask me for is to find CP to PD. So two ratios are given, and one ratio is asked. Now, what I do with the given ratios, I'm going to take them to my drawing, and I'm going to, that first one, which is a ratio of 2 to 3, I'm going to call the sides 2K and 3K. If there's a second ratio, you can't use K again. Then you must use a different variable, like a P, for instance. So let's do that. There's my triangle again. There's the ratio given to me. And now AD, I'm going to call it 2K. And DB, you expect already. And on your drawing, you must always fill this in. It makes it much easier. And that is 3K. All right, everyone clear? That comes from our very first discussion. So the moment that you've got a line and they say divide it in a ratio, you put the parts on, the 2K and the 3K. Now we've got another ratio, that BE equal to 4 over 3 EC. We're just going to divide by EC so that we can see the ratio clearly. So BE over EC, now you look at BE over EC. The BE part, BE will be 4 parts, the EC will be 3 parts. Please don't call it K. We used K already. Call it a different one. Now that one, I'm going to call it 4P. And that one, I'm going to call it 3P. So now you can see I've got all these parts on. Now the question is, what is that ratio? What is CP to PD? So just to take all this away, to make some space, now we're going to say, there's my question on the top. CP to PD, how do I get to that ratio? I am first of all going to look at that triangle, CDK, triangle CDK. When I work in that triangle, can you see there are two sides parallel, the EP and the KD, they are parallel. So that means I can, that ratio they ask me is part of that triangle, the CP to PD. And that will be equal to CE over EK. So let's write that. So that is the one that I'm looking for, CP over PD. What will that be equal to? And I must work with a triangle where the sides are parallel. So I go for this one, because those two sides are parallel, EP and
dk over that one. So you can clearly see the CP over PD will be equal to CE, which we have, over EK, which we don't have. The moment we can get EK, then we can find that ratio they ask us. So now our question is, how do we find EK or KE? So I wrote the ratio down. CP over PD is equal to 3P over EK. And that is our problem. What is that EK? The moment I can get that EK, I answered the question, because they just asked me to find the ratio. They didn't give me lengths here, so I'm going to get a ratio for an answer, not a length. So now how do we get to that one? So I take it to the right-hand side so that you keep an eye on what we are looking for. We are looking for EK. Now I must find a triangle where EK is in, because I'm looking for that. And I go for triangle ABE. Can you see the two sides parallel? KD and EA. So in that triangle, what do I have? I want EK. I've got the total. Now I do the same. Follow the parallel lines to D and to A. And what will you do? You will take the 2K and you will take the 5K. You can see there's the same ratio. Which one do I want? I want EK over the one I've got, 4P, is equal to the 2K over the one that I've got, and that is 5K if I add the two. Because it's K, I may add them. Now I write it down. EK is over 4P is equal to 2K over 5K. The K's will cancel. So that means, if I just clear it, and there it is again, I'm going to multiply by 4P. I'm going to cancel the K, and EK is that. And this EK, you now substitute into that right-hand side. You will see there I've marked it in blue to see this one. And then you will notice there I wrote it down again. The EK is not there. So now you will see the substitution happens. So now you've got 3P divided by 8P over 5. So you tip and times. It's just a little bit of algebra. And you multiply with the reciprocal. That's 5 over 8P. The P's will cancel. And you've got your ratio. So the ratio of CP to PD is 15 over 8. Or we can write it in that form as well. Either in fractions or as a ratio. Now, that is to give you an understanding of these first problems that we have on ratios. I want to discuss another example with you where we have parallel sides. But as you now can see in this example, that DE and AF are parallel, and then DF and AB are parallel. So now, what is given to us? A ratio, FE to EC, is 3 to 4. You will see them at the bottom of your drawing, FE to EC. So we can put down a 3K and a 4K. And then a question mark behind EC to BC. So there's my 3K. There is my 4K. Now they want EC, which we have, over BC, which we don't have, because we don't know the BF. So, because those sides are proportional, do you agree if FE will be proportional to AD? You can't use the same variable, so that will be 3P. And that will be 4P, because it's the same ratio. So that CE to EF will be the same ratio as CD to DA. You can't just use the same variable. So use the on one side K, on the other side P. So now what do we have? We want that EC over the BC, the top over the bottom. And that will be equal to EC to BC.
EC to BC will be equal to 4K over the BC, which I don't know. Now, how do I find? You can see I highlight that BC. How do I find that BC? That one. You see I put a question mark there. What is BC? The moment I can get BC, then I have the ratio they ask me. What is EC over BC? So what do we do? That is what I want. So now I need to find BC. So I work in triangle ABC. If I work in the big one, I work with AB parallel to DF. So which ratios I have? I have BC in that big triangle. That's the one that I want. Over the one that I've got is equal to the total over the top. And you agree we have, except for BC, we have the others. So I write it down. BC over FC is equal to AC over DC. And AC is 7P and DC is 4P. The P's will cancel. So that means BC over FC is equal to 7 over 4. Now, I just go back now to what I've done before. That is the BC that I'm looking for. I'm looking for the ratio EC to BC is 4K over BC. I found BC over FC, which is 7 over 4. Now, my problem is, what is that FC? And you agree with me, I multiply both sides. And my FC, if you look at the drawing, FC is 3K plus 4K, which is 7K. So it's 7 over 4 times 7K. That I multiplied there again for you. And that is now 49K over 4. Can you see that is the BC that I need for the left? So now you substitute it on the left-hand side. I'm just clearing the screen. That is what I want, that ratio. The BC is the one that troubles me, but I found BC to be that. And now you do a substitution. Put that blue into the blue. So, which means that EC over BC is 4K over 49K divided by 4. You tip and times, the K's will cancel, and you get your ratio. So the question was to find this ratio, and there we have the ratio. So, I hope that this is not too bad this far, that you are able to follow what I was trying to explain to you on this in terms of what we work with proportions. Now, I want to quickly discuss with you now 1 or 2 questions based on these slides that we just did. Remember, I told you that we have 2 sections that we're going to cover. The first section is on proportions. Now, just to remind you now again on what we said. What I was trying to explain to you with all of these slides is that if we have a triangle ABC and we draw a line parallel to that one, and this is say DE, then the sides are proportional. So that is what we just did there. Then we can say that AD, the top one, over DB, the bottom one, will be equal to AE over EC. Or what we can do as well is we can go for the total distance, total side, AB side, over the bottom one is DB, is equal to AC over, and that was DB at the bottom, so that is EC. At the moment a ratio is given to you, so if they give you a ratio of AB over, AD rather, over dB is equal to 2 over 3. Then we say that one is 2K, because of that AD is 2K, and dB will be 3K. And this side will have the same proportions, but you can't use K. So you can say these sides are 2P. Same as that, the 2, but with a P. This will be 3P, because those sides are proportional. Why? Your reason is those lines are parallel. So that is what the theorem tells us. If the lines are parallel, the sides are proportional. So with those discussions, I was trying to give you a little bit of a background on how to work with it. Let's now take a problem from one of our old exam papers, and let's see how they put these questions to you. There is a first question. And let's just leave the question first, that we just see what we have. You will now notice that I've got a big triangle here. In this big one, I've got those two sides parallel. Then I have another triangle here where those two sides are parallel. So the parallel sides always is the indication of your ratio. So if I look at this triangle, and that's why it's always important to say in which triangle are you working. And if I work in ACE, then that side over that will be equal to this over that. If I work in the big triangle, I work with that parallel sides, then this over that will be equal to this over that. And that is what you must always be careful. So they say to us in ADC, E is a point on AD and B is a point on AC, such that those are parallel. So we know that. F is a point there, such that those are parallel. It's also given to us that AB is equal to 2BC. Now, just before we do this question, I just want to clear this to you, because this is what the catch was in the problem. Because many students think that there's not a ratio given to you, and that is a ratio given to you. So if they say AB is equal to 2BC, what you do is you divide both sides by BC, so that you get the ratio of AB over BC. And that will be equal to 2 over 1. And look at that. And there you have a ratio. So they just try to hide it a little bit. So the ratio of AB to BC is 2 to 1. So this one you may call 2K, and this one is 1K, or you can just say K. So this AB to BC. Now this will be the same as this one, or you can say it's the same as that one. But you can't use K again. It now will depend on what they ask us. But it's always good to look at what is given to you. If you find your ratio, put it onto your drawing. Now let's see what they want from us. They say find AF over FE. Now, what is important here is that we first of all will say that for 9.1, we're going to work in triangle ACE. ACE. That's the triangle I'm going to work in. Now, what do I have? I know that AB over BC is equal to AF over FE. AB over BC is equal to AF over FE. You see, that's what they want. I can say this. Why can I say it? Because FB is parallel to EC. Those two sides are parallel. That's why, that is your reason. That's why you can say it. Now, what do we know about AB to BC? AB to BC. They've got a ratio of 2 to 1. So what is the ratio of AF over FE? They're also 2 over 1. If you put the K's, they will cancel, so it's 2 over 1. And then you can say AF to FE is equal to 2 to 1. If we just write it in that way, they ask us. So this is in a ratio form. This is in the fraction form. And that is my solution to this question. I hope you find this not too difficult. So just follow the parallel lines. If you have a ratio given You can put it in, and then you can calculate. Let's look at the second question. In the second question, they give us now a length. Remember now that first discussion we had. This length given to us is AF. So what they say is that AF, and you must now remember, this is a length. This is not a ratio like 2K and 1K. This is in millimeters. So this side, AF, this one, is 8 centimeters. You see, AF is 8 centimeters. Now they say find the length of ED. Find that length of ED. Now the question is, how will we do that? How will we find that? How will we solve this? So, if I just write this down to you in the second question, what do we have here? We know that AB over BC is 2 over 1. AB to BC is 2 over 1. So the first thing we're going to do is, we have that ratio, we have this length, we're going to find this length. So this is finally what they want us to find. Remember, ED is what I want to do. But to get to ED, I first need to find this FE. Now you can write down a ratio as you wish. So remember that we have a ratio there of 2 to 1. So I can now say the FE is what I'm looking for over the one that I know, which is AF, is equal to, so EF over the AF is equal to 1 over 2. 1 over 2. That's my ratio. Now, AF, you agree with me, that FE is over 8 is equal to a half. And if I multiply, I get this is 4 centimeters. So this side here, FE, is 4 centimeters. Remember, we are looking for this one. To get to this one, I need to work with those parallel lines. So I'm going to work in the big one. So how do I find that one now? So the first part was to find the length of this one. So you now agree with me that this total distance here is going to be 12 centimeters. That total distance will be 3K on that one, because I want ED. So let's write down, like we said before. What do we want? Let's call it DE or ED. What did they call it? ED. We say ED over the side that I have, and that is AE. So ED over AE, I follow the parallel lines, is equal to BC over AB. Why may I say that? Because those two lines are parallel. EB parallel to DC. This is what I want. Remember in the slides what I did? I highlighted this in like red for you. Over the one that I've got, parallel lines is this over that. Now, we now say that ED is what I'm looking for, over 12 is equal to, and now you can use only the ratios, or you can say 1K over 2K, but the K's will cancel. So we say ED is equal to a half times 12, and that is 6 centimeters. And there we solved this question. And I really hope that this is not too difficult. I'm not going to do very difficult ones with you. In the exam, these are the kind of questions they quite like to ask. You will see this question was worth 6 marks, and this is a typical question based only on grade 12 work from our old exam papers. And they always like to put like a grade 11 question, a grade 12 one, and then, of course, a mixed one, which are the ones you will do later. So always look at what ratio is given to you. Sometimes they hide it. Fill that in with a K or a P. If they give you a side, what is given, write down what is given to you, what do you get, and you write down the ratio. How do you get the ratios? By looking at the triangle you work in and which sides are parallel that you give as your reason. So, enough about this one. Let's look at another one. In this question 10 that you can see now, we again have a triangle where if you look at the big one, we have two sides parallel. And if you look at the smaller one, you have those two sides parallel. So again, you're going to look at what is given to you and what do they want from you. They say this is a point so that they are parallel. This is a point so that they are parallel. Now they say RT is equal to 6. So RT is 6 centimeters. You can see that's already written in on the drawing. And then they give us a ratio. WS to SP is 3 to 2. So that ratio WS, I can call it now 3K, and I can call it 2K. You remember from what I said right in the beginning. It makes life much easier if you do it this way. So can you see, if you look at this triangle here, those sides are parallel. Then this side over this one is equal to this over that. Because we've got the ratio there, we've got this one, that means we can find this one. So we can just say this over that is equal to this over that, and we can quickly calculate that one if necessary. So once we've got this one, it means we have the total one. Then we can go for the big one. That ratio is the same as this one over that one, and it means we can find this. So let's look what they want, and then we decide from there how we're going to approach it. They say exactly what I suggested we must find, and that is WT. So first of all, they want this side, WT. How will I write it down? Please remember, always, in particular in exams, that you first of all say, in triangle, because there's more than one, WPR or WRP is what I'm going to work in. And now in this triangle, what do I say? The one that I want, WT over TR, WT over TR is equal to WS over SP. Now, WT is what I want. TR is 6. WS is not 2, 3, but 3K. And this one is 2K. And the K's will cancel. So what is WT? Can I just move it up a little bit for you? And that is 3 over 2 times 6. And I think you will agree with me. This will be 2 goes into 6. 3 times 3 is 9 centimeters. And that is what this WT will be. So this one now we can say is 9 centimeters. And that's what I calculated in number 1. Now, what do they want in the second question? They ask you to find WQ, the total one. Now, to find the total one, WQ, you will agree it will most probably be easier to find RQ. Because if we can get RQ, I've got those two, then it means I can find WQ. So let's just write down that ratio first, where I look for this one. So how can I find RQ? I'm going to say I work in triangle PQW. And in this triangle, I have QR, this is what I want, over RW, which I've got. Those lines are parallel, is equal to 2K over 3K. So QR over RW, look at my parallel lines, I ignore those two now, work with these two. So this over that is this over that, because those lines are parallel, and that's what you will say now. that RS is parallel to QP. Now you say QR, the K's will cancel, is 2 over 3. Yeah, QR over RW is PS at the top over that, so it's the 2K over the 3K, times by RW, which is 15. So 3 goes into 15 5 times. 2 times 5 is 10 centimeters. So QR is 10 centimeters. So now, of course, we haven't answered the question yet. The question was WQ. But do you agree with me that's now easy? What is WQ? WQ or QW? WQ will be equal to 10 centimeters plus 6 centimeters plus 9 centimeters. And that gives you 19 plus 6 is 25 centimeters. And with that, we finished this question. And this is how sides divide other sides in the same proportion. So that is our first theorem in grade 12 that you're going to do. If two sides are parallel, they divide the other sides in the same proportion. They can give you a proportion. They can ask you to calculate a proportion. They can ask you to calculate lengths. And that is what we have up to here. Let's now take a break of 10 minutes up till around about 2 o'clock. And then when you come back, I will discuss with you the second theorem of grade 12. I see you then. Welcome back. I'm so proud of all of you who are still with me on this grade 12 geometry. This will really help you in the next term when you discuss this at school. In the previous session, I discussed with you the probability, not the probability, but the geometry of grade 12 based on the first theorem on proportions. So please remember, these proportions are true because there are two lines that's parallel. And those parallel lines always show you how to write down these proportions. In our second theorem that we're going to discuss, we're going to look at similarity. That is when two triangles are similar. And I want to talk to you about this for a moment. Don't confuse similar triangles with congruent triangles. In grade 9, grade 10, we used lots of congruent triangles, triangles that's congruent. If two triangles are congruent, it means they identical. The angles are equal, the sides are equal. So everything is equal. The two triangles are congruent. When we talk about similar triangles, we refer to triangles that's got the same shape, but not the same size. The one may be smaller than the other. And when will two triangles be similar? That is, if their angles are equal. You will remember the cases of congruency. Cases of congruency was like side, side, side. Side, angle, side, the included one. The right angle, the hypotenuse, and the side. Those were cases, the minimum conditions for congruency. When we look at similarity, two triangles similar, what we look for is angle, angle, angle. We want the angles to be equal. Now, how do we do that? If we have two triangles and we want to prove them similar, how do we do it? And I'm quickly going to show you on a piece of paper how we show two triangles similar. And then I'm going to show you a few slides that I prepared to show you all the nitty-gritty And to finish this, we're going to look at a few problems on this. So let's just look now at how this theorem works and what the theorem says. If I have two triangles, and let's say the one is ABC, and the other one is DEF. If we can show that this angle is equal to that one, and we can show this angle is equal to that one, and we can show this angle equal to that one, can you see the two triangles are now similar because the angles are equal? Now, how do we write it down? We say triangle ABC, so I go ABC, is similar. It's vertical, 3 vertical lines. You must remember congruency, horizontal lines 3, similar. And when you write this one down, it must be in the same order. So as the angles are equal. So A is equal to D, so A is first, so D is first. Then B is the same as E, so that means it must be E. C is the same as F, so that must be F. So what you will do in these questions, they will ask you to prove triangles similar, and we're going to use our geometry knowledge. Even the grade 11 work is now going to be part of it. Once we prove them similar, we write it down. We say these two are similar. Then they're going to ask you to find a proportion. Now, what I do, and I will show you on the slide as well, is that I call this frog face. So to find from the similar triangles, but it's important they must be in the correct order, you go the first two over the first two. So you say AB over DE. See, AB over DE is equal to, then we go BC over EF. BC over EF. Then we go AC over DF. AC over DF. Now I call this method frog face. You will see those two little things, and then I put the little eyes in. You will see later on, and it looks like a little frog. So just remember, once you prove your triangle similar, to find your ratios, you do frog face. So let's now go to our slides with this in mind. Remember, we want to prove triangles similar. Once they're similar, we can find the proportions. So let's see if we can do this and how I've done it for you in the slides. So as you can see on your screen, the heading is similarity, and I'm going to start with an example. So please keep in mind what I just discussed with you, that we want to prove triangles similar. So let's see what they want us to do in this problem. So they say to us, prove this triangle similar to that one. Now you must find the two triangles. PRQ, PRQ, you can see the Q is at the bottom, and then PST. That's what we want to prove similar. How do we do it? Let's make space. I say those two triangles I want similar, PRQ, PST. To prove similar, I need to prove the angles equal. So I say angle P from the first triangle, angle from that PRQ. What I'm basically doing, I'm writing down the angles from PRQ. So look at PRQ. P is the angle P. The angle R in that PRQ is R1. And the angle Q in triangle PRQ is Q2. So I put them on the left-hand side, below that triangle. So I want to see which ones to prove now equal. And now I go to PST. Remember, they already, if they're given to you like this, they're in the correct order. So on the right-hand side, so the PST triangle, look at PST. Angle P is angle P. Angle S will stay angle S, and angle T is angle T. Now, you agree with me that angle P is equal to angle P because it's a common one. Now, on the slides, I didn't put the reasons. I just draw a solid line to say those two, they are equal. I call it, I map them. And because I draw a solid line, it means I know, but when you do it, you must, of course, now put a reason. And the reason is it's a common angle. It belongs to both triangles. You can see what I've done. I've put down a little heart for you to say that those two, they belong together. They like in love. Then, R1, do you agree, is 90 degrees? Angle S is 90 degrees. So they are definitely equal because they're both 90. So you can just say both 90 degrees given as a reason. So they also a little couple. Now what about Q2 and T? Do we know if they are equal? No, we don't. Does it matter? No. Once you can prove two equal, the third group will be equal. Why? Because angles of a triangle is 180. So the moment that two of the angles are equal, the third ones must be equal. And you can see I give that one a gray line to say this one, we don't really know that they are equal, but we know because of angles of a triangle, there's not a specific reason. So that one is called our weakest link. So you only need to prove why I've done this. You don't need to do all of this. You can just say P is equal to P, a common angle, R1 is equal to S, 90 degrees given, Q2 is equal to T, and your reason is they are angles of a triangle is 180. I just gave it some names that it gives you a little bit of understanding. So we now prove those two triangles similar. So let's just clear it. Now the question is, find this ratio or this proportion. Now, to get this, we expect this must come from the triangles that we proved. So this is now my question. So what I do is I say those two triangles, PRQ, PST, they are similar. Now, I'm going to do frog face. Remember I told you earlier about my frog face. So I'm going to find, from these triangles, I'm going to find the proportions. And I'm going to see if I can't get what they ask me at the top. So it is PR over PS is equal to RQ over ST is equal to PQ over PT. Can you see the frog face? If you can't, I show you. There are the little eyes. You see it looks like a little frog? So PR over PS is equal to RQ over ST is equal to PQ over PT. So let's write it down. And there it's written. PR over PS is equal to RQ over ST is equal to PQ over PT. Can you see why it's so important that your order, when you write down your similar triangles, that the order must be correct? And this frog face is just an easy way to remember how to get your proportions. And it's the first two over the first two, the second two over the second two, and then the outer two over the outer two. Right, now we want to use these ratios to see if we can get the top one. Remember, if you look at the top of your page, they ask us to prove that ratio. How do we do it? We want to look at this one. Now, can you see in the one that we need to prove there's a RQ? In the one that we've got from the similar triangles, we've got an RQ. So what you do is you take a pencil and you circle them like I did. Then I look if that one's got a PQ, and there's a PQ as well. Then I look at the ST, and then I look at the PT. So as you can see, I'm going to use those two at the bottom that I highlighted now to get to the top one. So how do we do it? Now, if you look at the top one, there's not a multiplication. So it's not a matter of cross multiplication. It's RQ to PQ. And you will see ours at the bottom is written differently. It's RQ over ST. So what we need to do is we need to take ours, the one at the bottom, and there it is. I wrote it down. That is the one I'm going to use. and I just clear the page. So that is the one I'm going to use. The order is not exactly how I want it. So what I do is I cross multiply. RQ times PT is PQ times ST. Now, what ratio do I want? I want that PQ to be with RQ. So now I divide by PQ, I divide by PT, and I get that ratio. RQ over PQ is ST over PT, and now I can write it down. And that is what they ask me to prove. So, if we recap, what did they want you to do? They ask you to prove two triangles similar. Once you prove them similar by proving the angles equal, you use those similar triangles, you apply your frog face, then you get your ratios. You use those ratios to see which ones you need to prove whatever they ask you to prove. So that is what, in a nutshell, what similarity is all about. All right. So now I want us to look at a few questions where I'm going to discuss this with you. So I'm going to start with a question from the old exam papers, where you can see the one we just did was an easier one than this one, but it gives you exactly what we want to do. In this one, question 9, you can see they say there's a center O. You can see there's a circle, so grade 11 work is back. Is the center of the circle, this is perpendicular, that intersects. And now they ask you to, if this is 4x, what is that in terms of x? Then they say, prove these similar, like we just did. We're going to prove those triangles similar. We're going to use frog face. And then they give you something and they say, solve for x. So let's see what we have in this question. If O is the center, you will agree with me, there's a line drawn from a center of a circle perpendicular to a chord. So then you agree with me, the very first theorem of grade 11 apply, and those two parts are equal. So that we can say now. Anything else that we have here? That is a diameter, but there's not an angle in a semicircle. They are parallel given to us. Now that they say in the first question, they say to you that PS is 4x. PS is 4x. Do you agree both of them will be 2x? Now they say write down ST. ST in terms of x. ST will be 2x. So that is a very easy question for 1 mark. How will you write it down? It's always important that you make sure you know how to write this down. So to write this problem, what you will say is, in 9.1, is that you will say that PS is equal to 4x. They ask us for ST. Then you say ST is equal to 2x, and your reason is line from center perpendicular to chord bisect the chord. So therefore both are 2x. And that's all that you need to say. So it's 2x and 2x. Now, in our second part of the question, they ask us to prove triangle RST and triangle PKT. We must prove them similar. Those two triangles, we must prove them similar. Now, how do we prove these two triangles similar? Remember what I told you within the slides, that I take this triangle and I look for RST, and I say this is angle R, this is angle S, and now I don't know which T because they didn't number them for us. So that T we must now call RTS, RTS that we know. From this one, we expect that P to be the same as R because they're in the same order. So it will be P. we look at K, and then we also have an angle T, but this one is KTP. Now the question is, which angles do we know are equal? If I look at R and P, are those angles equal? And I can hear you say, definitely. Isn't that angles in the same segment, subtended by SK? Can you see? So R and P, well, definitely equal, and your reason is angles in the same segment. And now you can see why I told you during our discussion of grade 11 work, that if you can't do the grade 11 work, you will not cope with grade 12. Now we look for S and K. Do we know anything about S and K? Yes, we do. They subtended by that chord. You can see go to S, go to K. So they definitely equal, and they're also angles in the same segment. Now we only need to prove two of them. It's not necessary to prove the third one. But if I look at the third one, I talk about this angle and that one. And they definitely equal because they are vertical opposite angles. And you know vertical opposite angles, if two lines intersect, they are always equal. It's like you have two lines, those angles are equal. And they both equal to 90. So now what do we have? We have triangle RST similar to triangle PKT. PKT. And I write it down because the moment they say prove them similar, they must give it to you. So like it's given here, that order is correct already. So you must just make sure that you write it down correctly. Now that is all they wanted us to do in the second one. They only ask us to prove similar. Now, because they ask us to do something else, you will agree with me that in 9.3 we expect what we need to do here is to find maybe the proportions from this by using frog face. So let's just see what is given to us here. They say to us in number 3, if it is further given that TK is X and RT is 320, RT, this whole length is 320, and that is millimeters. So that is 320, that is X. Calculate the value of X. Now, what will we do? We are going to use now the similar triangles to find proportions and see if we can't use the proportions to solve for X, because I've got 3 sides that's equal to X and 1 side given to me. And these are now almost like the questions we did earlier. So I'm going to say in 9.3 that triangle RST is similar to triangle PKT. That is already proven. I don't need to say why, because we've done it already in the previous one. Now I'm going to use my frog face, and I say RS over PK is equal to ST over KT is equal to RT over PT. And that is what I have at the moment. Now, which sides do I have? So let's quickly have a look. What do I have? I have RT equal to 320 millimeters. You see the RT. I have ST equal to 2x. That's from this first triangle. From the other triangle, I've got PT equal to 2x. And I've got TK equal to x. So, can we now see where this will fit in? RT, is there a RT somewhere? Yes, I've got it there. You can see what I did earlier on the slides as well. An ST, I've got an ST. A PT, I've got a PT. A TK or a KT, I've got that. So can you see this is what I'm going to use? I'm not going to use that one. You mustn't scratch them like I did. Ne? It's just to show you. So you leave it there. You only use this one. So we say ST over, if you want to call it KT or TK, doesn't really matter. The order is equal to RT over PT. Let's just now substitute. So ST is 2x, KT is x, RT is 320, and PT is 2x. What you first of all will notice is that x and x will cancel. So we get 2 is equal to 320 over 2x. If I multiply both sides by 2x, then I will get 4x is equal to 320. I divide by 4, and x is equal to 80. And remember the units, this is millimeters. And there we've done our question. And isn't that lovely? Really such nice questions where it tests your grade 11 work. From grade 11, line drawn from a center of a circle, perpendicular to a chord, bisect, angles in the same segment. We use those two theorems to help us to solve this. We prove the triangles similar. Then we use the similar triangles to find our ratios. That is our ratios. We use our ratios to solve for x. And now you can see what really the purpose of all of this is. So I hope you find this as nice as I still do. These questions are really exciting, and once you start getting them correct, you will see it is really fun. Okay, let's now look at another one. And this question was out of a total of 7 marks. The next one is a little bit, ask us a little bit more than that. So let's see what this one is all about. This one is called question 9. You will see it almost looks like the grade 11 questions because of the circles and tangent. Looks like there's more than one tangent here. Looks like there's a couple of things, but let's discuss it first. So let's use our habit of not looking at the questions first, and let's see what we have before we start with this. They say in this diagram we have these two lines and they are both tangents. You can see there's no center given to us, so those 4 theorems are not here. There's no cyclic quad, so those theorems are out. So this problem is only on tangents. So we have the tan chord theorem. You can see that x and this y, we've got tan chord. But then, very important, we have 2 tangents. And you remember that theorem that says 2 tangents drawn from one point to a circle will be equal in length. And this one is crucial to remember. So this side is equal to that one. Remember that theorem? 2 tangents drawn to a circle, equal in length. You remember the 3 tangent theorems? The tan chord, the 2 tangents, and the radius perpendicular to a tangent. And in this one, we're going to use both of them. So this is a tangent, this is a chord. If I complete, this is y, then it means that angle is y. That one is x, that is the tangent and the chord, equal to the angle in the opposite segment. This one will be x. This angle here. These 2 sides are equal in length, so this triangle is isosceles, so that means that one is y. These 2 sides are equal because of the 2 tangents that's equal in length. This is y, so that one is y. So we can find quite a number of these now in terms of x and y. Can you remember the x and y are given to us? So let's look at the first question. This question is worth 6 marks, so you need to do a few things here. What do they say? Name with reasons 3 angles each equal to y. Not in terms of y, equal to y. Now, this hopefully you will find extremely easy. What do we know? We know that 2t is equal to y because that is given to us. Now, that doesn't count as the 3 angles, because that is given. We want another 3. If T2 is y, what is R2? You say R2 is equal to y, and your reason for that is the tan chord theorem. Then you say S2 is equal to y. And what is the reason? Isosceles triangle, and the reason is TR is equal to TS. TR equal to TS given. Two equal sides, then the two base angles are equal. Now I've got two already. Now I know for S3, and that is the one that many people forget. S3 is y, and why is that? Two tangents from one point equal in length. And that's what you need to say. And there are your three angles equal to y. The 6 marks, you get a mark for every angle. They will mark it like this, and you get a mark for every reason. And that gives you a total of 6. And it was not so difficult to answer these 6. But you will agree with me, this question is all grade 11 work. Even it's part of a grade 12. And that is where they start combining it, and that is where the questions become more difficult. So please be aware of this. Still remember how we did this, that you look if there's a center, 4 theorems. If there's a cyclic quad, 3 theorems. If there are tangents, 3 theorems. Which ones are there? Otherwise, you will miss this one if you don't do it. So it's very important. Let's look at the second question. In the second question, they ask you to prove two triangles similar. So we say, in triangle PRS and triangle PST. Now I'm just going to move it up so that we can see this. Now, if I look at PRS, PRS is that small little triangle, PRS. Angle P stays angle P. Angle R is R1. Angle S is S1. Is S1. Now I look for these triangles. They angle P, because it is now PST. ST is this one. PST. So P is P. S is 1 and 2. So it's S, 1 and 2. Let me just put the angles on. And the angle T is T1. You see, T1 is PST, that triangle. Now, which ones are equal? Those two are equal, and we say common. They are common angles. They belong to both triangles, so that means they must be equal. Now I need, between these two, I need another one. And can you see that one? Because it's indicated on your drawing. S1 is equal to T1. S1 is equal to T1 because they both equal to X because of the tan chord theorem. So they are equal. Will these two be equal? Yes. And you say angles of a triangle is equal to 180 degrees. So the third one we don't need to prove equal. It's not necessary. As long as we can prove two of them equal, the third one will be equal because of that. Now what we do is we say triangle, we know our order is correct. PRS is similar to triangle PST. And there we prove this question. Remember, they just ask you to prove the two triangles similar. Go and find the two triangles. Write down the angles of the one, the angles of the other. Go to your sketch. See if you can get them equal. Why? You only need to prove two of them. The third one will be equal. Put them in the same order. And what happens after this? We expect already the next question is about frog face. So let's have a look and see what do they want from us now. In this last part, they ask you to prove this ratio. Not quite the ratio, because they're already multiplied. So, to get to this, they want PS times RT equal to RS times PT. So this is what they ask us to prove. To get to this we need to look at our two triangles again. So this is what we want to prove. So prove that. Now, how will we do this? I'm just going to move it up that you can see clearly. So, first of all, we know that triangle. We proved it in the previous one. PRS is similar to triangle PST. I just want to see if I've got them correct. PRS, PST. They're in the correct order. Now, we're going to use our frog face. Because whatever they ask me to prove that looks like ratios, I'm going to apply frog face. So I say PR over PS is equal to RS over ST is equal to PS over PT. That is what I have from my frog face. Now the big question is, which ones must I use? You can see there's multiplication in. So somewhere they applied cross multiplication. So let's have a look and see if we have these required. So what I do is I look for PR. Do I have a PR there? And I don't. Or we can look the other way around. There's a PS that I want. There's a PS. There's a RT. RT or a TR. I can't find one. Then there's a RS. Then there's a PT. Then there's a PT. Anything else that I have? I just want to double check I didn't make any mistakes. I didn't. So, what do I do? Can you see there's a PS, but there's also a PS. You see that PS, I circled this one. But now I'm in 3 of them, but there's also a PS. So that means I'm going to use this one. So this ST is one that I don't have. They've got a PT, but I've got at least 3 of them. So what I will do is, I will now cross multiply to get as close to this. So you can see the RS and the PT. The RS and the PT is on the right-hand side. So I will multiply PS with ST, PS times ST. I will say it's equal to RS times PT. Now, when you compare this to what they want us to prove, you agree with me, PT we have. There's the PT. RS, I've got. RT, I don't have. PS, I've got. So this one I'm happy with. This one I'm happy with. This one I'm happy with. This ST one is my problem. How do I get rid of the ST? They want a RT. So let's get back to our drawing. Remember, we've got the ST. We don't want the ST. What do we want? If I can put it here on the side, I want a RT. Now, what do I know about ST? ST. Can you see ST is the same as RT? They're given equal right at the top. So ST and RT are the same. So now I say, but ST is equal to RT. And that is given. So therefore, PS times RT is equal to RS times PT. And there we've got exactly what they ask us to prove. So if you look at this last one, they say PS times PT is equal to RS times PT. This is RT, and that is PT. So we proved it. How did we do this? We took the triangles that we proved similar. We applied our frog face. We look what they want. We circle those. If one of them you can't get, don't get a fright. It's always this kind of case where this side is equal to another one. Cross multiply, whatever they want you to do. Look at the ones that you want. You don't care about them. look at the one you don't want, go back to your drawing, see if you can find something equal to that. So now, that gives you a good idea of what the grade 12 work is all about. So, this is our last question for today. On the geometry, I hope this is going to help you not only to do the grade 11 geometry, but also to be ready for this beautiful topic of grade 12. I will be back with you on Thursday, where we will discuss a very important topic for your matric exams, and that is functions. Also, sometimes people refer to it as graphs. The correct name, functions, and I'm going to discuss with you all the different functions that you need to know for your grade 12 exam. I hope on Thursday, as from 9 o'clock, you will join me again. Until then, all of the best.